So is it visible, sir? Hello?
Yeah, it's not as full screen is not
Okay,
available.
yeah, I will, sir, your good name, sir?
You are not in projection mode as yet, looks like.
Rajesh, sir.
Okay.
I will just send it, sir. 1 second.
Now?
Yes, now yes.
Rajesh, sir.
Okay. Okay, sir.
Okay, good.
Link भेजना webinar से.
So you will talk about the
मेरा फोन में email
aim of the webinar. Okay, you have modified this. Okay. And you have one thing about the about the group. Bandyopadhyay ji, about the group also you wanted something.
Expert group, na, sir?
Expert group, yeah. You have to introduce the expert group also.
Yeah, that is there, na, sir? Inside here, if you see.
Now, what are the objectives of the expert group?
Yeah, that is also there.
So that flyer, where is it?
So it
to the INI expert group. We will be commencing the webinar in another couple of minutes. Thank you very much.
Good news. చూసారు ఆల్రెడీ ఇవాళ రేపు రేపు ఫ్రైడే కదా లేదు వెహికల్ మన వెహికల్ తీసుకుని వెళ్దాం రేపు వెళ్దాం కానీ టెన్షన్ ఊరిలో వస్తాను
Yeah, good afternoon, everybody. Thank you for your patience. So, and welcome to the INA expert group on RF microwave and terahertz wave webinar. And we have a very good set of speakers and panelists uh, who would be interacting during this webinar. And we would also be taking some questions from the audience or some queries in that case. And any audience members would like to interact or something, you can always please put on the chat box. So with that, we will now commence our webinar. I hope I am audible. And to start with the webinar, I will invite Professor Sanket Goyal, Dean Sponsored Research and Consultancy Division, BITS Pilani, to please start the webinar with a welcome address. Professor Sanket.
Thank you, Professor Harish Dikshit. It's an honor for me to be a part of this esteemed dignitaries from many leading institutes in India. So I would like to say good afternoon to all of you. I am delighted to participate in this very interesting webinar on strategy for growth of RF microwave to terahertz technology and industry in India. I'm happy to know that this is organized by INA Group on Advanced Microwave Terahertz Technology and Application team, as well as other institutes like Siri Pilani, Samir Mumbai, SAC Ahmedabad, and of course BITS Pilani Hyderabad campus. I believe this initiative to frame a position paper for RF and microwave technology in our country to chart the roadmap for the growth is an extremely welcome step. This is so because of its importance for several strategic, commercial, and societal programs. And because of this fact, I believe that such paper will help to frame future policies around these programs. It is important to frame such policies keeping in mind the perspectives from various academic labs, industries, students, and many working professionals, and of course, the expert group working in this area in the right direction. The involvement of several academic research organizations and industries cutting across several sub-areas of microwave engineering and terahertz technologies, it also a very significant and denotes the interest of RF and microwave in our country. I believe that such deliberation under the guidance of eminent expert group is a need of the hour, considering the initiatives by our government like Self-Reliant India, Atmanirbhar Bharat. As an institute, BITS Pilani, we are delighted to be a part of the organizing committee, given that we have significant work going on in this area in all the three campuses, Indian campuses. At Hyderabad, which has a thriving microwave group within EEE department and some of it cross department as well. And we have generated significant facilities to carry out research work in RF and microwave area. Just to add, we are in the process to establish a high power microwave test setup, which would be one of the very few in the world, especially in the academic institutions. Students from various institutes and startups are welcome to use such facility, and they can certainly get in touch with Professor Lilith Kumar, Professor Harish Dikshit, and so on. Without taking too much time, I wish the webinar a grand success and hope you have fruitful deliberations. Thank you so much.
Thank you very much, Professor Goyal, for your welcome address. I would now like to invite Dr. Bandopadhyay from CSIR Siri Pilani to please convene, and also convener of the INA expert group, to please address the audience and talk about the INA expert group. Dr. Bandopadhyay.
Thank you, Professor Dikshit. So this is my privilege to talk about the webinar and the INA expert group. Sir, I want to share a PPT, just a one slide. So here it is saying that yeah, okay,
Yeah, you can now share, sir.
okay. So a very good afternoon to all the dignitaries and all the present in this webinar. So this current webinar is on the strategy for growth of RF and microwave to terahertz technology and industry in India. This is being organized on the banner of INA expert group on advanced microwave terahertz technology and applications. The INA expert group is chaired by Professor Lalit Kumar and Dr. Shashank Chaturvedi, Director of IPR Gandhinagar, Dr. Nilesh Desai, Director SAC Ahmedabad, Dr. A.T. Kalagatki, Director Antiques Corporations, and all the other members, the galaxy of members are esteemed members are there. So the goal of this expert group is to evolve a position paper on advanced microwave, millimeter wave, and terahertz wave technology and applications, and come out with the recommendation, technology roadmap, and strategies for self-reliance. Because we all know that this technologies, the advanced microwave terahertz technologies, is the technology which is coming up right now, and will be driving the growth of the country maybe for the next decade. So this is a very extremely important area of research and technology. And that's why to know our strengths and know our challenges, this type of position paper is very important. So on this line, already two webinars have been conducted. So once to chalk out what is the needs of what we need to include in the curriculum for this technology to flourish, and also the application sides, what are the strategy for growth. So in this series, this is the third webinar, which is basically aimed on R&D and industry. So here we want to provide a platform for interaction with the R&D and technology leaders and the industry, and to have an overview of the strength, weakness, and challenges and future outlook of growth. And then we can have also the trends and status of the development of indigenous technologies and products, and to access the resource requirements for financial, technological, HR. So this is being organized on the banner of the INA expert group together with CSIR Pilani, BITS Pilani, Hyderabad campus, Samir Mumbai, and SAC Ahmedabad. So with this, there are five talks which will be followed by a panel discussion. So I welcome you all for this webinar, and uh, and wish all the success for the webinar. Thank you.
Thank you, Dr. Ayan, for your address. I would now like to invite Professor Lalit Kumar, chairperson of the INA expert group, to please address the gathering.
Well, thank you, Dr. Harish. I'm very happy that today we are all gathered to have this third webinar of the INA expert group. And my task has been simplified by Dr. Sanket Goyal as well as Dr. Bandyopadhyay to really tell you that what is the genesis of this webinar and the expert group. Now, I'm also very indebted at the outset. I would like to, in fact, express my thanks to all the participating organizations, the organizers, Siri Pilani, BITS Hyderabad, SAC Ahmedabad, Samir Mumbai, and all our organizations which are where our expert members come from. And all those who have been supporting and have joined this webinar, I am thankful to them. As regards the theme of this webinar, I think it's very, very important. All of you know that we are in India and also globally having the microwaves touching all aspects of our life. Maybe it is communication, it is entertainment, it is health, it is energy, and domestic heating and industrial heating and so on. Apart from that, the microwave have already invaded our life, but now the overcrowding of the microwave spectrum is leading us to look elsewhere in the higher frequency domain. So millimeter wave is an area now which is also being coming up, and you might have heard in the recent times that the 5G is already getting into millimeter waves and 6G will go even beyond. But apart from that, we are getting into millimeter wave imaging for security, millimeter wave imaging for the satellite imagery, for defense as well as civilian applications, millimeter wave radars for collision avoidance, autonomous vehicles, and in a big way, the millimeter waves are coming. And of late, for about last 2 decades, there is a lot of interest in the terahertz wave technology because these technologies or these frequencies offer a vast opportunity of huge data communication, unlimited bandwidth, covert communication. They have a very good property that they get attenuated at a very heavily. So if we are having a communication, it cannot be eavesdropped like in other frequencies. It will go over only a short distance and will be then attenuated significantly. Nobody can overhear that. Apart from that, it has also its applications in defense and security, that it can provide you a signature of the material, a blueprint or a fingerprint of the material of contraband material, explosives, and so on. And that gives a lot of impetus for the applications in security and in millimeter wave terahertz imaging in security as well as in medical applications and all such areas. So looking at these three technologies, we find that India has a vast and a long tradition in microwave engineering. Many of the institutions, when I looked at a survey, hundreds of institutions in India are teaching microwaves and so on. Even though we lament that students don't want to learn microwave. But in spite of that, MTech programs, PhD programs and research programs are going on in this area. And I think India is very well poised to make a dent in this technology on the world scene. And this is the objective of our group, to put together, collate that kind of a strength and try to recommend to the government to bring in proper policy changes and use a conducive environment, funding and all kind of things, whatever needed to nurture this area so that it becomes the future technology area and engine of national growth. One of the things I would also like to mention, our institution IPR is working on that. The energy, which we call clean energy, is going to only come from fusion. And fusion is driven by millimeter wave gyrotrons. And these are the devices which currently are now powering up a experimental thermonuclear or fusion reactor in France. And that reactor will be replicated, and hope in the next 20 years we'll have, other than the nuclear energy, we'll have fusion reactors coming very soon. And those will be all powered by the millimeter wave devices like gyrotron. So this is only one example. In space communication, I think you will hear Rajiv Jyoti and others who also talk about the space. Millimeters are going to dominate in a big way. In security, they are going to dominate. In medical applications, the millimeter wave and terahertz will dominate. So this is the century which was going to be not like the past centuries was electricity. This century is going to be dominated by electromagnetic radiations. That's what is my feeling. So I request all of you to please help the group, the expert group, with your ideas and opinions. And this webinar is only a beginning. It's going to be encouraging you to think about this and contribute further with your ideas to help and strengthen the knowledge of the group, to be able to make right presentation, recommendations to the government and the policy making bodies about the future and the interventions required in this technology area. So without taking much time, I would now, I am also looking forward that our organizers have assembled a galaxy of eminent experts in this area, Dr. Rajiv Jyoti from InSpace, Dr. Shinde from Industry Extra Microwave, and Dr. Anant Nayak from GETEC, Dr. Reddy, who is now from MTRDC, DRDO, is also interested in agriculture applications, Dr. Arjit Majumdar from Samir will be on millimeter wave, and Dr. Prabhu on spectroscopy from TIFR. And we have then a panel of well-known, eminent industrialists from Bell, ECIL, and many private industries. Director Siri Pilani also will be participating at some stage. And I'm very happy that Dr. A.K. Singh will be chairing that session. He has the distinction of working both in LRD, the LAR lab, and the DLRL, the EW lab. And he has a vast experience in the area of the defense applications. And so we look forward to, and I see a number of young panelists in the panel discussion which is going to take place. And so we are looking forward to a very enriching and educational experience for this afternoon. And please join all of you in good strength with us and help us serve the cause of the expert group and the nation towards Atmanirbhar Bharat in the area of microwave, millimeter wave, and terahertz technology. And let us try to make equipments, apparatus, and devices in India, for India, and maybe for the world. Thank you very much.
Thank you, Professor Lal Kumar. We now will move on towards our technical sessions. And to coordinate our first technical session, I would like to invite Dr. Bera from CSIR, Siri Pilani, to please coordinate this technical session and take it forward from here. Dr. Bera.
Yeah. Okay, good afternoon to all. Hello, am I audible?
Yes, you are audible, sir.
Okay, fine. Okay, now
Vera, sir, I think your audio has gone.
Dr. Rajiv Jyoti, I would like to give brief introduction. Dr. Rajiv Jyoti is a distinguished scientist and director IN Space, ISRO. He is an expert on microwave antenna system, communication satellite systems, and microwave sensors. He is recipient of 10 awards and author of more than 150 papers and 14 patents in his credit. He is UN ESA Fellow and ESTEC ESA. He has made outstanding contribution in antenna system for all of the SATCOM and navigation and microwave remote sensing payload and antenna systems of more than 25 communication and navigational payload in INSAT and GSAT and IRMS programs. He also received 2010 and 2040 ISRO Team Excellence Award as a team leader. Now I am inviting Dr. Rajiv Jyoti to deliver his to chair this session. So, sir, please.
Thank you, Dr. Bera. I hope I am audible. Can somebody confirm?
Yes, sir, you're audible.
Yeah, okay. Yeah. So, very good afternoon to all the participants and the organizers and all the esteemed guests here, invited speakers. At the outset, let me thank Dr. Lalit and Dr. Bandyopadhyay for inviting me for chairing this session. And really, I'm glad to hear the session is very interesting, and wherein you have created a platform where researchers, the DRDO labs, and industry partners, and the INE, which is binding everybody, they are forming a one unique platform, wherein all the discussions which will be useful for making a white paper will be created here. So I'm very seeing very interesting session here going to happen in the next 2 hours. And definitely a lot of significant work has been done in this area, which is called microwave and RF microwave and terahertz. And a lot of work, not only in the government sector, even in industry, has happened over the years. I myself is a product of Delhi University, where in the first time the microwave course was started by then our head of the department in North Delhi campus, that is Dr. GP Srivastava. That was one of the unique. Now I am seeing there are a lot of other universities like BHU and Kharagpur IIT and many other places. We have core group where the microwave is imparted to the even at the education level. And I'm seeing that a lot of experts are there from Samir, SAC, Siri Pilani, who are the pioneer in their field in the microwave. And DRDO is also there, as you said, Dr. Lalit Kumar mentioned about the AK thing. I think these people also have done very good amount of work. So, and I want to just show one slide, one or two, because yesterday when I was talking to Dr. Lalit, he requested me to show whether if you can, I don't know, somebody has to enable that to one or two slides. I will be just, can somebody remove this slide, which is right now there, so that I can share mine?
Yeah, sir. 1 minute.
Okay.
Yeah.
So, today, as Dr. Lalit mentioned, that today everywhere the main thing is that we need to you cannot share co-host or presenter has to make you a presenter.
Sir, you should be able to share now, sir. Please check.
Yeah. Now it is there.
Yeah.
So okay. Today, as Dr. Lalit ji mentioned that today everywhere people are moving from low spectrum L band to S band. We are shifting toward even in microwave satellite communication also up to Q and V band. And millimeter frequency, sub-millimeter frequency is by choice of its behavior. It has a lot of application, not only which we talk about security systems and all that, even to get a humidity sounders in the for atmosphere for data for which will be very useful parameter for IMD for getting their calibration channels in the localized region. So because of the property of it get absorbed in those channels, the very fine channels are there. And apart from that, imaging, which is normally happens in any, it can be by processing data and then whether for anti-collision radars or for any other medical, space science, food, there are quantum physics. And now people talking about quantum communication, and wherein a lot of work is being done right now in not in the industry, but definitely we have seen that some startups and some IISc, Indian Institute of Science, and in IIT Madras, this work is going on, where the encryption and optical systems and are also are being currently carried out. And a lot of work is required because we are running out of spectrum, and then overcrowding is happening at the low frequency. And this particular slide, I just want to give a glimpse of what is happening even in spacebound. The Herschel telescope, which was launched after 15 years in 2009, a lot of work has happened, which is going to give a lot more cosmic science, which will be available to our scientists to understand the whole universe for exploration. So that is one which is going, and I think for that. Our own in the country, the astrophysical this IAA and Bangalore and other some people are working. Even ISRO has also started talking about now the telescope, and for it to start with the ground-based telescopes are also very interesting because currently not a single telescope is available in this part of the galactic region wherein mapping can be done in this Asian, because lot of are there in the even in China that it is not there. It is only available in this region where in US and Atlanta and all those region. Japan has, I think. So there is a lot of possibility in exploring this particular band to even measure the carbon monoxide in different region, and in currently ISRO Space Application Center, from where I spent 35 years. We started the project to put up a telescope on this place, Henley, because that suits the requirement in terms of dry atmosphere and the humidity is very low. And so that is work is already being going on, and technology is required in getting those mixers and all those things. And the current trend is that even not only from ground, even for the CubeSat sounders, which is also recently, I think 1 month, 15 days back only, the launch was there from satellite from ISRO, that is SSLV, and wherein one of the CubeSat as experimental with the hardware which was made for mapping the ground from the ground base system, it has been put on board, and a lot of data is available now in these frequencies, even at 187, 183 gigahertz. So this will be a useful wherein the telescope has been built, the Cassegrain geometry, the Gregorian geometry, and then the whole thing has been scaled to ruggedized for airborne and for the spaceborne. Now, the thumb millimeter, which is very interesting, and over the years, this has seen that lot of, I will not go into those, but definitely the technology which is required for microwave is different, and for the terahertz, when it goes to some millimeter and all that, becomes a totally different ball game, and we have to develop a detectors and go for those type of systems which can be which can be cooled to that temperature, wherein the noise level of that can be detected, so that we can detect the very those signals and bring it back to a low band and digitize them and keep it, and a lot of information can be there. And there is a lot of science data which is even interest from other countries also, if this is being used in this region, whether for astronomy or for meteorology or for planetary exploration. And I must say that I'll not talk, because I know that a lot of the talk is going to be given by those I've seen. All of are known to me, Dr. Shinde and Anant Naik, who is working on various microwave and those frequencies, the MMICs and subsystems and all that. So they will be talking about that. But I just want to make a few lines on what InSpace is doing. InSpace is creating a ecosystem for the space system, wherein any non-government entities, because wherein they are not able to spend a lot of, because this requires any work which you need to do on a microwave or some millimeter or millimeter or higher frequency tera, you need a lot of capex is required, and a lot of design tools are required. So if any such things are, we have to enable the young, the skilled manpower we have to generate, and we have to ensure that the industry also participate, which is the right topic of today's from Indian industry perspective. So for enabling them, how to facilitate those people and they can work. The talent is there, but the capex, because of capex which is available only in the government, cannot be, they get deprived and they are not able to leapfrog. So to make a conducive atmosphere, the InSpace is created, wherein we are creating a lot of facilities in the country which can be used by non-government entities. Like I can give you one example, but the one other example is that for any space gear, but this is for only space-based microwave or terahertz or all those hardwares. So we are right now, design center is coming up with all the softwares in Ahmedabad, wherein all which are required very much to at least whatever innovative idea somebody has, how to convert into a meaningful product before it get realized, and how to do all simulations, whether it's electrical or mechanical, or if power wise or low noise, what all those products can be analyzed. So we have put something like center which is going to be available from the next month, that is from April, to all the non-government organizations and non-government entities, and will be can be used by reaching out to us on our digital platform. And apart from that, the skill manpower also, for skilling, we are interacting with many of the in microwave and in other region also, like talking about launch vehicle and all that, where the avionics requirement of for the launch vehicle. And for capacity building, we are also seeing what devices, like what we are talking about today, the device as well as the subsystem requirement. So a lot of problems can be solved if we have to be a leader in this region. A lot of work is being done. We are importing a lot of components from outside, and then we are building a subsystems. So if we work on devices critical, which are low hanging fruit for us, like active and passive technologies which can be built with the we aggregate the requirement and understand which are those which are required on a various across the sectors, not only for space, not only for ground, not only for medical use, not only for the defense application. So if we aggregate those requirements and some meaningful model can be made in terms of marketing, not only the Indian market, but also taking care of the outside country. We can export these items also instead of using it here only. And second is for the subsystems which are required, if any handholding is required in miniaturization, which I know our panel's speakers will talk about. Those things also can be tested, and some limited facilities we are creating in the Ahmedabad in-space headquarters, which we are trying to replicate where other places also, so that the microwave, millimeter, and all other frequencies which are required for our space utilization. And there is a thin line difference between space and the ground, but all these for space use can be enabled through a in-space facility. So that's what I thought I'll give emphasis. I will not be justifying if I only talk about the millimeter. And I think this is a very important point to make sure that we are going into a microwave thrusters, microwave, all those which are required even for the launch vehicle, like an electronic. Also, we need thrusters for propulsion even. So all those things as IPR is doing. So similar things has a lot of opportunities are there. And I think the sky is the limit. And we need to make sure that all this can be facilitated. And I'm looking forward for this session to generate, to help and understand myself also that what are the areas which are required to be more focused and more to ensure that we have a Atmanirbharta in India. Thank you. Thank you, sir. That's all.
Okay. Thank you, sir, for your nice and insightful presentation. So, first lecture of this session from Dr. G.R. Sinde. So, his topic is infrastructure and manpower for microwave industries. So, before inviting him for his address, I am going to give some brief introduction about Dr. G.R. Sinde. Dr. G.R. Sinde have over 30 years of experience in designing strategic electronics and systems for the space and defense sector. His portfolio spans from 10 megahertz to 40 gigahertz band, with projects such as TR modules for radar and remote sensing satellites, LNS, PLOs, receivers, and converter for GSAT series communication satellites, and exciter receivers and TR module for missile applications. He is currently the Senior General Manager of Space Group at Astra Microwave Products Limited. He has earlier worked in Space Application Center, Ahmedabad, and EMC Technologies, Montreal, Canada. So now I invite Dr. G.R. Sinde for his address. Please, sir.
Namaste. Dr. Biradi, thank you for that introduction. Humble submission to the august audience is I'm not doctor by degree, and I don't have any presentation as such for my and audience convenience. So I'm going to be short, but yes, through the journey of my work of 35 years in RF and microwave, from government organization to private organizations, what I have seen, I would like to present, keeping the view with respect to the infrastructure and manpower. It is natural that each institute wants to grow. It is natural that each company would like to grow. But when we talk about the niche areas like millimeter waves or the very high frequency, we should also see that the infrastructure is effectively utilized. I feel that this concept was there with us previously and is being utilized at least by Western or European countries quite nicely. And it surely, if you permit me to state that, if we want to be Sarve Bhavantu Sukhina, then we will surely have to start with the Om Sahana Vavatu. We will have to come together and do it if we want to really have a good return on every investment we do. You see that if I have to talk about the domain, naturally we are looking for a very high frequency, so we will probably need probe stations. We'll look for an automated assembly line. Probably we have foundry within a country. We'll need EMI/MC test facilities. We'll need packaging. We'll need vector network analyzers, spectrum analyzers, waveguide assemblies, and cal kits. Now, if you see at this frequency range, when somebody wants to work, the amount of investment a company or an institute will do and the amount of work they will try to do on that, if you see the utilization ratio, I am sure, at least my perception says that our ratio is 3% utilization, which is far below than expected. The percentage which I have arrived at based on the way I am seeing the industries around me or the institutes around me and they utilizing their instruments. So no offense, disclaimer is just presenting an idea how the infrastructure should be brought in and utilized. When we move to such a high frequency range, surely the infrastructure will demand. Say, for example, we have a GETEC, which is a foundry within a country. But I, as an AMPL, I would like to submit that, okay, I hardly use some components from GETEC. Now, unless I use components, GETEC will not flourish. And unless GETEC doesn't flourish, I will not get new components from GETEC. So it's a Jivasya Jivanam situation. We need to depend on each other and try to encourage each other. So the first thing is we need to come together. Then only we can improve our return on investment. I am sure, because with every infrastructure comes manpower. Say, if we have a probe station, it's not just to have a probe station. You need a person who is trained, who is exploring a probe station to do the appropriate measurements with appropriate skills and efficiency. Then only the confidence for the measurements carried out by that person will be useful. Otherwise, his probe may not be positioned properly, his data may not come to us properly, and then we may tend to conclude something which is not the actual situation. So the infrastructure, which is higher end, and the manpower, which also needs a training and exploration, goes hand in hand. So as I have listed out, say when we are trying to use the calkit, waveguide calkit with the VNAs, which will span till the frequency range of say maybe 1 terahertz or further, you will need all that precision assemblies, understanding. So the person who is utilizing the instrument needs to be trained. So we can have the facility, like we have facilities for EMI/MC, but people are not there to understand how to utilize the facility. Facility is existing. So we need to have a good balance between the infrastructure and manpower. So I feel that if we have a infrastructure which is created on a sharing basis, and then probably one can afford to have a dedicated person, because there are examples, I will not quote the locations, that the infrastructure has been created, it was utilized for a period of year or two, and after that it is now looking for a job, that's that level of job for that infrastructure being utilized. And because there is no job, the skilled person who was associated with that particular infrastructure has been moved to somewhere else, so he is no more exploring that infrastructure. So when the actual need will come, the efficiency with which that infrastructure should be utilized will not happen because the person has been away from that infrastructure. So he has not explored, he has not kept it running. So we have an operational cost, we have calibration cost, we have calculate cost, and we have a configuration. See, there are a variety of configurations. When the instruments get complicated, the configurations also need to be managed properly. So I think the responsibility lies on all of us that we need to create an infrastructure which is utilized by many, and we need to create a manpower at that infrastructure location which becomes expert in utilizing it. I think with this I present my viewpoint that how infrastructure and industry can contribute to this development. I thank all the dignitaries for the opportunity. Thank you very much.
Thank you, sir, for your nice address. So, any queries from audience?
Shinde, you have Rajiv here. You have only addressed the infrastructure and the manpower, the skilled manpower and the operational thing. Anything on the technology, whether you also talked about, of course, about the GATEC, that MMICs and all that which are required. But anything on the technology side on, you want to say anything?
Sir, no, sir, I believe that Nayak sir will be covering that because he's going to speak with respect to boundary and his subject is also there. So I restricted myself to the clear infrastructure and manpower.
Okay.
Yeah. Thank you. Thank you.
Shinde, I would like to ask
Yes.
that can you tell what are the hold-ups for the industry if you want to grow in this area of microwave, millimeter wave? What are the challenges to grow? What are the restrictions because of which you are not able to do as much as you would like to? Any comment on that?
Yes, sir. Actually, I did, while presenting the infrastructure, I did present that challenge area. As you see, suppose I wish to enter and have an infrastructure in a domain of millimeter wave or the very high frequencies, sub-Tera as well. The type of subsystems which I'm going to roll out over here, maybe one or two. So my utilization of the tools and infrastructure is going to be far less than 3%, and it may not fetch me a return on investment. And today, our operational structure is we are trying to compete with each other instead of complementing with each other. So that competition is, indirectly hitting somewhere on the pricing, and then we would not like to do that. So I accept that the major attitude among us is competitive, not complementing. That's the one thing I think we need to bring change, and that's why I said Sahana also. Yeah.
Okay, thank you.
Thank you.
Any queries? No? If not, then let's thanks to our speaker, Dr. G.R. Sinde. Now, our next speaker of this particular session, Dr. Anant Naik. So, before his address, I am going to give the brief introduction of Dr. Naik. Dr. Naik is currently CEO of Gallium Arsenide Enabling Technology Center. We all know it as a GATEC, Hyderabad, India. His area of interest are gallium arsenide integrated circuit design, integrated circuit packaging, HEMT integrated circuit, cavity resonators, microwave limiters, microwave receivers, microwave switch, millimeter wave amplifier, multi-chip module, and semiconductor devices modeling. So with this brief introduction, I am inviting Dr. Naik to address his talk. So Dr. Naik, please.
Yeah. Am I audible now?
Yes, sir, you are audible.
Okay, thank you. You almost read the profile of my colleague, Dr. Sandeep. I am a basically semiconductor specialist and technologist. Anyway, but being a CEO, I am quite aware of all the areas that you just now brought about. So, as first of all, good afternoon to Dr. Professor Lalit Kumarji, Professor Harish, and all at BITS Hyderabad campus, Pilani campus, and my warm regards to Rajivji also, who has been working with GATEC for quite long time, and also like Sindeji said, he is also the one who is supporting all these activities in millimeter wave, microwave through various projects, sharing technology, developing technology, and then space qualifying GATEC in the past. So ISRO and DRDO combined has definitely helped the industry in general. And I think, yeah, definitely we need to work more. As far as Sindeji's this request is that, yes, we are actually working very closely with the AMPL also, and supporting each other. In fact, quite a lot can still be done. And I think we have very excellent relation with the AMPL. So there is a hidden competition, but we are no match in size to AMPL. But our expertise in semiconductor is something unique. So yes, definitely we can work really very hard. And also, to other my co-panelists or co-speakers, particularly Uma Maestro Reddy ji, with whom we worked a lot on KU and SSPA at GATEC for MTRDC, and he has been a good supporter of GATEC from DRDO side also. So that's all. I think this is to begin with. Briefly about GATEC, and I take this presentation as Professor Lalit Kumari said, is a first of such kind activity. And because we are already involved with some of the discussion that is taken place at JATC, IIT also. They are also having some kind of a terahertz, particularly for communication kind of a drive. So I think this is also a good initiative, and we should complement and put up a combined picture to government. And in this, I think my main aim would be to what GATEC is doing and what are the competence. And yes, we have initiated into the terahertz technology again through a development order from Space Application Center for Schottky barrier detector diodes up to 3 terahertz for their deep space application. And of course, mixer and other applications that both the teams are working on that also now. We already released the PDK for the same, and I think SSPL, GATEC and Space SAC team is working together to refine it and make a terahertz MMIC application specific MMICs. So I think let us take this opportunity to introduce GATEC, and let us see in what way we can work together among various participants today here, and we can definitely add more industries and universities, institutes. I think we have enough competence everywhere scattered, and there is a need to channelize it. That's what I can say. So, for example, GATEC is a part of DRDO, and that we initiated around 30 plus years ago by DRDO proposing GATEC for MMIC applications as that were denied at that point in time to India. So, our for previous chairpersons and said to RM, they proposed that we should have an enabling center, and this is how GATEC came into being. And we had some primitive initial technology from SSPL, which got productionized at GATEC, where SCL they've created the facility and handed over to DRDO after 5-6 years of operation. And subsequently, our facility has been qualified for space application by SAC Ahmedabad, very close working with the team, qualification team, and the microwave team there at SAC, and ultimately we became space qualified in 2004. And ever since we've been working together various satellite missions, and GATEC has been providing various chips, MMIC chips and modules and MCMs to SAC for various missions. So yeah, there is a micro ecosystem is still existing in India by way of research, users and the fab. And now the government is definitely putting a lot of money into the semiconductor ecosystem. And yeah, there will be, I think, maybe 5 years, 10 years time, so that ecosystem actually comes up in India. It will take some time, but yeah, there is a good initial move has been made by the government. So I would focus only on the compound semiconductor times. So terahertz is a huge and vast technology area. I mean to say, right from generation to detection to amplification and some specific applications, mixer, etc. So I will only touch upon the production and fabrication side of this, that to a semiconductor approach. And what I know about what SSPL is also working on the terahertz detector technology in using a CNT or nanotubes, carbon nanotube based selector plus MEMS based terahertz detectors have just been demonstrated by SSPL last year. So now we are trying to convert into a FPA kind of a setup using that MEMS based terahertz sensors. So people are working.
I think there seems to be some connectivity issues. We'll just wait for a couple of minutes.
I think there is some issue with the voice communication from Dr. Nayak. We are trying to sort it out.
Yeah, there is some technical issue on Dr. Anant Naik's side. He could be joining back in a minute.
I think it will take Dr. Nayak to take a minute. In the meantime, anybody feels compelled to make a small, short, very short comment, then please raise your hand, then we'll make you unmute. So, Dr. Surendpal, please, we'll welcome your comment.
Yeah, Dr. Lalit Kumar, Dr. Nayak has presented, but I think he was not in the picture. GATEC supplied in 99-2000 some devices to us, which were space qualified in TES satellite, which was our first, what we call it, a spy satellite, post Kargil. It was made in the small time duration of 18 months at the advice of then Prime Minister Vajpayee ji. And GATEC devices were used because we could not get the devices from outside. So GATEC made the devices for us. And you may be knowing that my classmate and friend, late Dr. Hanuman Prasad Vyas, was at that time involved in it. And he promised that he will get the X-band devices, including the modulator. So maybe Dr. Nayak can make some corrections that this GATEC was space qualified even 99-2000 itself, not in 2004. 2004, when RI set was done, where Rajiv was involved and Rana, Rajiv, Dr. Sharma, they were involved, Tapan Mishra, then it was formally qualified. Thank you. This was a comment, positive comment I wanted to give for GATEC. I also wish to say that DRDO does not use GATEC that much as ISRO uses. We have used GATEC later on also. Both RI is Space Application Center as well as URSC, then ISRO Satellite Center, where I was heading the communication activities. Thank you.
Yeah, DRDO works for everyone.
You give us appreciation that ISRO used it, your facilities, which you are still not using it. Although I'm
We
also
believe,
part of DRDO now.
yes, yes, of course. We believe in charity. So I would like Dr. A.K. Singh, I see here. Dr. A.K. Singh, would you like to make a brief comment? Your session will start later, but maybe now if you want to make anything on the topic, please, can you unmute him? Dr. A.K. Singh. To hear, I think is there. Left. I see he is not there now. Dr. Chandrasekhar, are you there, sir? I would very much request you to make a brief comment on the topic. You have to unmute him from here.
I'm sorry to disturb you, but I represent the industry. And my name is Munish Bhandari. We make microwaves for medical industry, and we are part of the Summit transfer of technology. So let me know when I can have a little interface for 4 to 5 minutes where we could talk about the challenges that the industry faces.
That's the topic for the panel discussion, and definitely
we are not part of the panel for some reason, but we were recommended by Professor K.P. Ray because we developed these microwave for medical industry since 2006.
Now, the panel discussion will definitely invite people from the floor, so you will be definitely invited there. Huh?
What time would that be, sir? Sorry for disturbing you. What time would that be?
4:45.
Yeah, panel discussion would commence around 4:45 p.m., sir.
All right. Thank you very much. Thank you for your time.
Yeah.
I think I would request the chairman to please move to the next speaker, Dr. Reddy. And we will ask Dr. Nayak to join back when his technical problem
Yeah.
is sorted.
Okay. Yeah, I think I agree with you. Maybe I think I'll request Bera to he can invite the next speaker.
Yes, sure, sir. Okay. So our next speaker is Dr. S.U.M. Reddy. Actually, he is very well-known personality in microwave devices area, though it's my duty to give some formal introduction about Dr. Reddy. But Dr. Reddy is a former director of Microwave Tube Research and Development Center, MTRDC. This is a defense research laboratory. His research area is in computer-aided design and development of helix and coupled cavity traveling wave tubes. Dr. Reddy was the recipient of DRDO Scientist Award in the year of 2001 and the DRDO Agni Award for Excellence in Self-Reliance in 2003. He is a fellow of Vacuum Electron Devices and Applications Society and member of Magnetic Society of India. So with this brief introduction, I invite Dr. Reddy to deliver his address. Reddy sir, please.
Thank you, Dr. Bera. At the outset, I'd like to thank Dr. Lalit Kumar and the INA team for giving me an opportunity to present what is close to my heart. Even though I worked for defense for 35 years, this is close to my heart. How agriculture use can be there for microwaves. So that is why from this thing, I am going to touch upon the few of the only interesting things about the requirements of our industry. I think there is a lot of potential which is not even explored. Only maybe few percentage only I explored the potential of the microwaves. I'm talking about the conventional microwaves up to 10 gigahertz. From this, we can see there is a. I'm going to touch upon few of the applications. That itself shows there is huge potential for the industry to enter into this field and do a lot of research as well as production into the work. So I think let me share my slides. So I have to share.
Dr. Reddy, first you show your face, slightly tilt the camera.
Okay, sir.
Yeah, now we can see you better. Yes.
Yes, sir.
Yeah, thank you.
The share option has gone from my laptop. I'm sharing my screen.
Sir, we can see your screen, sir.
But I go to share option.
Sir, please open your file. That's all. Your screen already has been shared. Now we are seeing your screen. So you just open your PPT file so we can see.
Okay, let me see.
Yeah.
Now you are able to see?
Yes, sir.
Yeah. So I think thank you, Vera, for the introduction. For the new members of the group, I want to say I am O.S. Reddy, retired as a director of MTRDC, which is a DRDO lab. And now I am working as a consultant to Messrs. Versabyte Data Systems Private Limited. So they are the mainly manufacturing of power supplies for defense industry. But now we are planning to enter into the field of microwave tubes, particularly the TWTs. So as I told, some of the applications up to conventional, up to 10 gigahertz, I am going to highlight. So one of the applications is the drying of chilies using microwaves. So chilies contain 70 to 80% of water. So they cannot be stored for long because water content is high. So what we should do, we have to remove the water content. So drying of chilies is important for storing them. So sun drying is widely used in India. I think all of us know that the field the farmers will be putting them and it will be dried for few days. But requires long time and humidity and temperature fluctuations result in loss of color and loss of flavor. So is there any alternative? So people have come out with, so there is a danger of loss of product if it rains during this period. There is a big danger actually, many farmers face this problem. So what is the solution? So people have come up with the solution. Hot air drying is faster than sun drying, but a chilli surface is smooth without any porosity. So hot air cannot penetrate the surface of chilli, takes time to consume and consumes high energy and hence not cost effective. So microwaves drying is fast and can overcome these problems. So what is the water content finally we are looking for is 8 to 10%. So the time comparison for chilies dried in sun and microwaves, you can see the first graph shows about 2,500 to 3,000 minutes required to dry in sun. That is 3 to 4 days will be required. And when it comes to microwave, maybe 30 to 40 minutes is enough to dry the chilies in the microwave. So we can see these are fresh chilies, and when dried in air, the color they have decolored so much, whereas in the microwave the discoloration is not that much. So there is advantage, and flavor also can be retained in microwave better than in sun drying. Sun drying takes 3 to 4 days. So microwave drying only takes 30 to 40 minutes. So in India, the quantity of chili grown is about 17.9 lakh tons is grown in India. If only 20% of the crop is dried by microwaves, that is 3.0 lakh tons. So crop fruiting period is around 3 months, maybe from December to March, April it will be there. So assuming we have got an industrial oven which can process 0.5 tons per day. So one machine can process 45 tons in one season. That means the number of machines required is around 8,000 machines are required. So huge potential for the industry for this application. That is, you have to make magnetrons, make a micro system and components for this. So it is a huge business potential for the industry to look into this. So the reference paper I have given from where I have taken these details. And this is one of the industrial equipment, industrial oven that has been manufactured by Ferrite Microwave Technologies. I think they are using for multiple applications. They are heating cereals also. Along with that, they are doing multiple work on using this equipment. I think Samir Mumbai also has transfer technology for similar equipments to industry for manufacture. So this is some of the salient features of the drying equipment. So finally, what he says is what he claims is increases efficiency, decreases energy usage, and reduce cost, increase throughput and flexibility through instantaneous control. And the advantage of this unit is maybe in the fruiting period of chilies, it can be used for for drying chilies, but it can be other periods it can be used for multiple areas of work. So this is the advantage of such machine. So this is one of the applications where I have seen a lot of potential for industry to do the work. And similarly, weed management is one of the things in the agriculture field. We can see when we go to the field, there is a lot of weed grown, which is not required, which is detrimental to the crop. And also in the urban areas also we'll see if there is a vacant site near to our house, so there is a lot of weed growing in that and is uncontrollable. And if you remove by manual means, within the next rain it comes again. So it is a big problem. So I think some Australian researcher has found a technology using microwaves how this weed control can be done. We can see in the conventional way, we till the soil and in the sun, and then the weeds will dry, but that will not remove the seeds completely. So what Australian researcher has done is to the tractor he has put a microwave system where conventional microwaves he has taken output of the microwave and radiated using a small antenna to the weed. So that will dry the weeds. So this Australian engineer invented a micro-powered weed killer that cooks unwanted vegetation with electromagnetic energy. It is on its way to commercialization. It is in the research, they are doing the commercialization part of it. His name is Graham Bordy. He is working in the University of Melbourne. So the name of the equipment he has named it as Microwave, and it gives microwaves and removes the ungerminated seeds also along with the weed. That is which is germinated and grown plant also it can remove, and the seeds which are there in the soil also removes. That's why once maybe 2-3 times you apply this microwave, the total weed seed is totally removed and it will not come up again. This is the advantage of using this technology. The microwave energy heats up the vegetation, creating internal steam until the cell walls break, and crackling, popping, and hissing sounds emanate from the weeds in his demonstration videos. He has demonstrated, it seems. So this is the figure shows where they have applied the microwave this thing to the weed, grown weed, and the patch where microwave is applied, you can see it is totally dried. And what they have found, they have applied this microwave as well as compared the different things for the untreated weed when it is growing in the field. What is the yield of the farm field is only 0.55 or something. When herbicides are used, that is the chemicals are used, it is slightly increased. But I think now all of us know the chemicals are so dangerous for human beings as well as soil also get damaged. So hand weeding is one of the things widely used when crop is there, but that is going to be very costly. Now the labor cost has increased so much, so it is becoming detrimental to the farmers. But that is increased a little bit the yield, whereas the microwave has increased the yield by 10%. So that shows the advantage of using microwave this thing to weed control. So this is another application where we can see a lot of potential for the industry to go into this area. And yesterday I saw on news, onion price in Maharashtra is 2 rupees per kg, and the onion price in Italy is 1200 rupees per kg. So this crisis we are hearing alternate years, the same crisis will be coming. So many farmers are even committing suicide because of this. So our technology, microwave technology, give any solution for this? Yes, there is a solution for this. There is a huge export potential for dried onion slices as well as dried onion powder. It can be preserved for few years. This powder and slices can be preserved for few years, up to 1 year after unpacking the pack. So that means there is a large potential to store and export and use this for the commercial use. So micro driving and sterilization comes in handy for this application. The annual potential for the onion powder is there for the worldwide. The business market is around 11.02 billions. It is expected to grow at 6% per year, and it is going to touch 11.02 billion by 2020. It is a huge potential they are expecting. And apart from dried onion powder, dried onion slices also exported. The average market price for dried onion slice is about 50 rupees in India. India exported 8.2 lakhs of dried onion slices in 2018. I think maybe $11 million. The top countries which are importing dried onions from India are Germany, USA, Russia. These are the main importers from India, the onion slices. It's already being done, but there is a huge potential for further enhancement in the market. So this is one of the unit being produced by Onion Process. The name of the company is Onion Process. So I think this is a huge drying and sterilization machine. This is called automatic drying and sterilization machine, used to dry and sterilize onion powder and onion slice flakes. This is a tunnel type machine. Also can be used for drying and sterilizing teas, herbs, flowers, green leaves, and so multiple use. It can be used for multiple applications. And sterilization done at a low temperature of 55 to 75 degrees centigrade. Hence, it retains the original nutrition and color and taste. So machines available to process 20 kg to 300 kg per hour, and the power requirements varies from 20 kilowatts to 300 kilowatts. It is all done by our conventional microwave ovens frequencies. So temperature control is less than 1 degree per centigrade. Other application, what I am seeing is pest control by microwaves. Is it possible? So I think all of us know we are using a lot of pesticides in all the crops what we grow, and we are consuming them. So I think it is estimated because of this, cancer is going to grow, and our population is going to be troubled by cancer in the next decades. So this is the alternative. So microwaves maybe come in our help for this killing insects by microwaves. So if you see the metabolism is a limited temperature environment and they are cold-blooded. These insects are cold-blooded. So body temperature is determined by climate conditions in their immediate environment. The possible approach to pest control is raise the insect body temperature to lethal levels. So radiating RF waves is one of the methods to increase body temperature of insects. Power, wavelength, and polarization between the energy coupled to the body of the insect. So further studies required for commercial use of this. So this is I could not get the satisfactory literature for supporting. Yes, this can be used in commercial grade. In the laboratory, and this is definitely they have used and it is proved successful. But for commercial application, still a lot of research is required. I think R&D institutions and universities can take up this research how to do this pest control work and see the scope of work for industry in microwave technologies. So magnetron development is there. Output power ranges from 1 kilowatt to 1 megawatt. So many devices, so variations of powers are required. And frequency, mostly they are using 915 megahertz and 2.45 gigahertz. And micro components are also required for this. Power combiners, loads, circulators, etc. are also required for this meeting these requirements. And if you see applications along with food market, that is foam drying, food processing, meat tempering, textile and fabric industry, bacon processing, chemical heating, industrial material processing, biosolids and biomass treatment, oil and coal treatment, fluid and liquid treatment, and microwave assisted extraction. So many applications are there. Very only I have highlighted a few of them. A lot of potential for the industry to look into this. I think we have not even explored the tip of the iceberg. So much potential is there. So with this, I thank the organizers once again. Thank you, sir.
Yeah, I have a question to you, Rajesh.
Yes, sir.
Here. This you are told that 220 kilowatt to 300 kilowatt type of power requirement is there, and you mentioned that for all these agri tech type of application,
Yes,
you are talking about S-band, maybe normal microwave frequencies, correct?
One 915 megahertz is one frequency, and 2.45 gigahertz is other frequency. These two frequencies are mostly used for the industry.
In the country, who is doing this particular research work for making?
I think Samir has done this work, and similar equipment what I have shown the ferrite industry. Similar equipment TOT has been done by Samir to industry.
No, I'm not talking about the development of the instrument. I'm talking about the which band is required for what application. Like you told, host of application, whether it's for textile or for food processing, oil and coal treatment, and all these things which are I'm seeing.
Yes.
Any idea about that? Who is doing this? Basic which frequencies are required, what power requirements are there? When you talk about
only I have collected information where I spoke about the applications I spoke. That is 915 megahertz and 2.45. But mostly 2.45 used in many of the applications with various power levels. Depending on the quantity to be treated per hour, they increase the power or the size of the equipment.
Sir, I'd like to interject here. We are from the industry and we are using 2.45 gigahertz for hospital linen drying. Hospital linen drying.
Okay.
So we are developing this device for export markets, and we also use the same frequency for sterilizing medical waste on a conveyor belt.
Yeah.
So we are developing these technologies. We have a notified body CE on the existing machine that we took from Samir about 10 years ago. But the gentleman asked about the frequency, what we are using is 2.45 free bandwidth. Sir.
Yeah.
Thank you.
Thank you.
Okay.
Yeah, thank you.
Now my question was that on viruses and all those things, whether such things can be used for new areas rather what?
I think there is only some research is required, sir.
Okay.
Because
no, sir,
the insects are having different sizes. Small, maybe less than 0.1 millimeter to very big size, maybe 1 centimeter also. So there only research is required. What is suited for what type of insect pest control?
Correct. But my last question
So for
to
the
you is
viruses,
anybody
we
can
are
answer, maybe
using
from the industry
3.45,
point of
and
view.
we've been
What is the
validated by ICMR for sterilization. We've achieved log 8, log 9 sterilization. We are validated by AIMS New Delhi, AIMS Jodhpur, as well as ICMR.
what is
Oh,
the
thank you, sir.
total market capacity in terms of volume wise for this requirement? Is it very aggressively being used, this equipment, and what is the market size for this type of product?
So this is massive because
Now,
you know
massively,
this
can
is
you quantify what is the number? And
I
are
can
we importing it,
we
or
have
are we making it all the requirement through our Indian localization?
no, sir, we are exporting this to Europe also. We've exported about 15 machines to Europe 2 years ago. We have more than 250 installations of microwave in the country. We have almost 85 to 90% of the market share in the country. And all the aims today in the country, all of them are using microwave as the method of sterilization of medical waste. That is the most basic. I mean, you can put it to linen disinfection,
Okay.
you
Yeah.
can a lot of use it. But
Yeah.
there
Thank
is
you.
one serious problem which we'll discuss once we come on the open forum, sir.
Okay.
Thank you. Thank you.
Thank you, sir.
That was very informative, Dr. Reddy. I'm so impressed with the kind of work you've done. We would possibly connect with you offline, and I'm
Yes,
sure.
sir, definitely. Yeah, I'll be glad to work with you, sir. Yeah.
My pleasure, sir. Thank you so much, Dr. Reddy.
Maybe I think, Vera, if no other question, you can go to the next speaker, or if Anant Naik is there, then we can.
I have joined back.
Okay. Yeah, please. Anandji,
I think sharing is to be moved.
you have to
Yeah.
you have to improve RF microwave RF connectivity at your end.
This is the BSNL. Can't help it. Yeah. So I think anyway, we already had a brief introduction plus some. Yeah, there you go. Is it visible now?
Yes, sir.
So yeah. So anyway, so this is what I was at this slide. So the GETEC is the only foundry as such today in India which is having a small scale production of compound semiconductor MMICs, gallium nitride, gallium arsenide, and now also we have entered into this terahertz chip making, terahertz component making. So we are evolving process technologies for fabricating these devices. And maybe in the slides to come, I will show the kind of work that we have done till now. So if you see the microwave, now this is microwave to terahertz market. So this is a old report which says both gallium arsenide as well as gallium nitride market are growing extremely fast. And whereas gallium nitride is growing significantly for power applications, gallium arsenide is still holding the fort with the same kind of volume requirement. It's not, there was a belief that gallium nitride would eventually replace gallium arsenide, but then that's not happening so soon now. So by 2025, both the markets will increase. However, CAGR will be little less for gallium arsenide market. So anyway, for about GETEC, now GETEC is a kind of IDM foundry, and we also give the foundry PDKs to various users, and who can design their chips on our PDK, and then we can make fabricate the ICs, characterize it, qualify it for various levels, mill as well as space levels, and this is our model of operation. Now we have got all the facilities right from material deposition, material growth in by way of MBE. A lot of materials also we import it also, which are based on MOCVD or gallium nitride material as of today. We do plan to have gallium nitride growth facility soon in next 2 years or so. We have a complete fab facility with 0.1 micron feature size gates for MMICs and various gallium nitride and gallium arsenide low noise devices. And we also have complete design modeling team and facility to make the models and designs, and measurement facility. So it's a totally vertically integrated facility, but at a lower scale, and it's a particularly used for captive use for mostly DRDO and ISRO. So this is our fab tools. Basically, some of the critical tools are only showing here. It's very difficult to show complete because it's almost 15,000 plus square feet of clean room area, and we've got electron beam lithography system, various ICPRIs, PECVD, ICP-CVDs, various spray etching tools, and characterized FESAM, as well as production level PR coaters, developers, and all sort of metallization other things are available at GATEC. And these are some of the reliability tools that we regularly use for space qualifications. And a lot of support and facilities come sometimes shared with AMPL as and when they require, they use our facility. If we require, we use their facility if the system is down. So because we are in proximity, so we do interact with them. And this facility can have all the tools required for getting a space qualified MMIC to the satisfaction of quality team of SAC Ahmedabad. This is RF characterization tool, right from load pole, low parametric noise parameter measurement system, and automatic RF prober for wafer mapping, which are essential for during production. This is only a glimpse of the technology that we have got. This is the mushroom gate technology which we employ to our gallium arsenide SPM as well as gallium nitride devices. And the minimum feature is 0.13 micron. So the FT for this is almost into 90 to 100 gigahertz, and it's good enough to work working MMIC up to carbon. So we have got various other technologies now, and we also have right now around 150 plus design IPs which are fabricated at GATEC and which cater to various application bands like DA, DPS, oscillators, multipliers. Because oscillators, multipliers are going to play a bigger role in the terahertz range when we want to have some low terahertz application by multiplying the signal that is generated by MMICs. And this out of 150 plus MMIC, a lot of them are space heritage MMICs, which are used designed by also SAC Ahmedabad, and which has been used in various satellite systems from RISAT series satellite to Cartosat to Chandrayaan missions and all. So some of the pictures now I'm not showing because some of them are also closely developed with SAC, and the proprietary rights exist with SAC Ahmedabad. This is only one of the chip that we have developed for wideband core chip. A foundry's maturity can be maybe thought of by the way they can use the best fabrication facility to achieve this kind of a application circuits like core chip. So we have got C-band core chip for space application, which will probably be used by SAC in the time to come. We have got 5 to 18 gigahertz very wide band front end chip, which will be used. Beamforming chip, which will be possibly used by our EW system laboratories. And this is designed for a particular application which cannot be named as of now. So these are all designed, fabricated at GATEC and qualified. With that, there is one more critical circuit, I would say, which is a bidirectional amplifier, which is designed at GATEC, and then which will be find good application in the ISR radar system as a signal dividing and multiplication in the backside of the ISR radar front end. So these are all in-house developments, possibly used only by the DRDO. So we also have a big program on gallium nitride. Right now we have got 50 volt process for up to S band and L band, which has 10 to 11 watts per mm power density, and 5 to 6 watt at 28 volt for X band applications. We also demonstrated 0.15 micron GaN devices with almost 45 gigahertz cutoff, but unless we qualify it, we do not call it as a readily available technology. However, it has been demonstrated a couple of times. So now coming to the terahertz today's discussion, we have initiated this activity with support from SAC Ahmedabad, a team who funded this activity for terahertz Schottky barrier detector diode. So it has been to start with, there are various terahertz sources and generators. I think this is too insignificant a slide for the present audience because this is just initiation. So right now we are working with the detector diodes, and now we have got likely to get a tech project development project from SSPL Delhi for PCS based terahertz generation and detection module or a diode or a system, I would say. So that we are taking up at GATEC. So this will be 2 products available at GATEC. So in a terahertz Schottky diode, that can either be used for multipliers or mixers and all. And this is a schematic of a gallium arsenide diode, which employs air bridge connections to lower the parasitics in the system in the diode, so that it can cross 2 to 3 gigahertz frequency. And these are only this is one of the example which we have taken from Ericsson and Mr. Reference with NR Ericsson, which they have used it for multipliers, because multiplier is one of the most important thing for terahertz generation also. So and that this FESAM picture is the device that we have made at GATEC. It is around 10 mask process with a very multiple coated multi-level resist system for air bridge creation, electroplating, characterization, everything that can be required for a low parasitic device. So besides that multiplier, there is an application in mixer, which I think SAC team and GATEC team will work on that, and we have released our PDK and AD, which is based on ADS for the Schottky diodes, as well as the parasitic elements that may be required for mixer application. So this will be like in next 6 to 7 months, we should be able to have some first-end MMIC based on terahertz Schottky diode, which will be fabricated at GATEC, designed by SAC Ahmedabad, and maybe GATEC design team also will be involved in that. So this is how we developed this thing. We got input from SAC that we certainly want a certain kind of device parameters. So our MB team simulated the epi structure on Atlas. We have this MB system from Wraith. Our team optimized the growth process. They have grown the structures here. And now then we have processed around 7 to 8 wafers till date. And we have finalized our epi structure with collaborated with our simulation, and various configuration of these devices are made, which is anti-parallel, back-to-back, single diode, and this is almost kind of a rectifier configuration, which has been realized along with the various other passive structures. So this has a FT of around 2.3 terahertz, and this is the model that our team developed at GATEC. We did have inputs, and we did our measurement at IIT Delhi also for 110 up to 110 gigahertz test system at CARE, and our next wafer is also will be sent to along with my team to IIT Delhi for this RF on wafer RF measurement work. So these are the simulation results of this developed diodes, and which is matched completely with the model as well as measured values. So now this Schottky small signal model is incorporated on ADS, and now it is available as an element on ADS tool. So if some user wants with the proper NDA, we can share these details with the user for their application or their own designs. So what next we are proposing at GATEC, because GATEC is into the fabrication technology. We will have a certain direction to meet our terahertz requirement for various users. Not all the areas can be covered by us. So right now with SSPL Delhi, who has a backup with us for R&D backup, and GATEC and SSPL Delhi team do work together jointly to implement and develop this technology. So there are 2 things that we are in the pipeline. One is the terahertz generation and detection using PCA-based system. So this project is now sanctioned, and this development activity will be carried out at GATEC. It involves around very difficult epi design, which is LT gallium arsenide, LT in case combination of structures, which is simulation is being done right now, and the process steps are now being developed at GATEC. So this is our next aim, and I think within a year or so we should be able to demonstrate this device at GATEC. And besides this, we are also working with Department of Atomic Energy to have a very high energy pulse width PCA, which is a different structure and a different material. So, but that I cannot disclose right now because of other, I would say, information controlled development. And this is just an explanation how a photodetector will work. I think, again, this may not be of much use to the present audience because they all know most of these things. Another technology that we look forward to develop is the indium phosphide or gallium arsenide hemp based transistors, which has an FT of more than 1 terahertz at 0.15 micron. Having all this technique of fabrication these devices, the underneath material is now being simulated, and this hemp structures will be then attempted at GATEC MB. So already work is in a very advanced stage because incorporating an indium into the extent of 50+% is extremely challenging task for MB epi developer. So I think we have almost reached those development stages, and maybe in the next year and a half we should demonstrate our first device made at GATEC. So this will actually enhance a lot of competence in terahertz technology. Besides this, okay, thanks for this. But besides that, our competence and developing new technologies, any industry or institute working in a different area can also jointly work with us and fund a project to GATEC so that we can evolve the technology and realize those devices. This is a unique facility, and I think a lot can be done. As proved by ISRO and DRDO, who consistently uses this facility. And like Sindhji said, yes, private players are also most welcome. To begin with, being a small foundry, it may not be very economical, but yes, indigenous and self-reliant is more important than economics. Thank you. Any questions?
Actually, very informative. It refreshed my interaction with you. Okay, when I was in SAC. So,
right.
yeah. So, what anyhow, most of the things what you told, I knew area was that
Yes,
Schottky based diode and all that which you are working. That's a very good that because now you had a issue of micro machining at the substrate. That was the issue which was there earlier probably.
Now we are
you overcome that.
Now we are actually trying for the beam lead approach also.
Beam lead approach. Okay. No, but there I have one question. See, two questions. One is on your regular, which Dr. Siddhapar also was mentioning about when you were not there, that the low frequencies MMICs which are being used, and you are also going for 10 to 12, 13 chips integrating into a system on your chip. Those things are available. Now, these are we using this for any commercial apart from ISRO and DRDO?
No, I think, sir, yeah, volume wise, for example, volume wise, we cannot have those volumes if we want to. ISRO requirements are quantitatively little
that is
less.
space qualified.
Yeah.
There may be some requirement even for non-space qualified also, because medical equipment and all other things which will be requiring.
Wherever there is a volume, so volume handling, for example, we have proposed the government of India, DRDO, to put in some money to have a 6-inch fab now, because this was a state-of-the-art fab when we initiated around 25-26 years ago. And to meet the volume, we need a 6-inch fab, so which discussions are going on.
Okay, because
so definitely it will be commercially available.
Yeah. Yes. Okay, so what I'm saying is a lot of, I think this has a potential, this technology, even for locomotives and as well as for the this all collision avoidance systems which are required at low frequencies. So those, I don't know whether they are commercial. So that's my point. So second thing is on the higher frequencies, now terahertz going on beyond. So now Schottky barrier diode types of whatever converter mixers we are making. Apart from that, there is also a requirement of 4-degree Kelvin technology, wherein they are able to have this noise temperature of 100 Kelvin.
Okay.
There, the SIS technology is used, that semiconductor insulators and semiconductor, that
Okay,
SIS.
bonded.
So that also will be the requirement if we have to capture the higher advanced studies which are required for our scientific community. So
Right, right.
that also, if you whether you have any plan or towards that side to that area.
Right now, yeah,
For
right now we
telescope
are
development and all those things which are required, like our
yeah.
US has sent, and we also are planning now telescope for exploration for that type of application.
So right now, what we are actually going incrementally. So right now, our focus is on W band MMICs and above terahertz. And whereas the low temperature, if some technology inputs are given by any institute, and if we have the tool, process expertise is always there at GETEC because they are very trained
I think
manpower.
this requirement is there for the both IAE and our IAA, and even the SAC also was discussing when I was there. We were interacting with few universities in US where they have developed such processes, which is, it looks like that volume will not be large,
Yeah.
which will be only for scientific, but it will be a specialized. So that area
That
also
can be
has to
taken up. Yes, of course, we can take up with some input from SAC as well as maybe DRDO.
But that will be required even for
Definitely.
security requirement which are coming for airport and all those things which are
Yes, yes.
JPL is working.
The potential is there for automotive as well as 5G
Yeah.
and all those things, whatever technology band that we serve. But then the catering in a volume, I think that is a different ball game together. Yeah.
Yeah. Okay. Maybe I think over to Behraj. Maybe you can ask question from anybody from participant.
Dr. Rajiv, I just want to make a comment and ask a query to Dr. Nayak. You mentioned that the facility can be offered to academics. So if some academic institutes, for example, designs a device, but does not have the money to produce it at your place, do you think you can still support it?
Depend, because this semiconductor is a very expensive thing, as you know. Even processing one wafer
I know, that's what I'm
cost
asking.
15 lakh rupees or so. So what I think we can work out and have some funding where we can have a pizza mask. Some institute can put in the device, and the GETEC can also be supported. And processing wise, everybody gets some use of this application. So long back we have supported, proposed to all the IITs earlier. That one can have an approach, but yes, some funding has to come because we are a commercial operation.
Yeah,
not
understood.
only,
But you can pitch in part of the cost.
no problem. Yeah, definitely.
Okay. Thank you.
It would be a good idea if one can do that. Thank you.
Okay. Thank you, sir. Any other queries from audience? Sir, I have just one query.
Yeah.
Actually, now we are starting to designing some solid state amplifier kind of thing, and for that we need some device. Let's I give you an example. Simple industrial band 2.45 gigahertz. If we want some device from GETEC, is it possible to?
What power level?
That may be, of course, that for industrial application, power requirement is 100, maybe more than 100 watt.
100 watt. Yeah, I think right now we are working on gallium nitride based devices, and we already have demonstrated 100 some watt in L and S band. But yes, that is, I think, within a couple of months down line, I think we should be able to give 100 plus watts of gallium nitride device in up to L and S band.
Oh. And sir, another thing is to design that we need, of course, we need that ADS file, what you mentioned.
PDK, that is PDK we develop. Yes.
So that kind of file also.
Yeah, in PDK, as I said, PDK can be shared with an NDA. And since this is DRDO, there is right now, we have to also know the application and where the product that is made out of it will be exported, which country or something, if you are exporting it. So that kind of some initial information will be required. Definitely.
Actually, we are from Research Institute, CSIR. So maybe that kind of NDA can be formulated.
Yeah, no issue. We have given this PDK to SAC also. We have given PDK to some of the IITs also. AMPL also has our PDK. So,
Okay.
but only they have to use it only for DRDO ISRO applications.
Okay. Okay. Thank you.
Okay, thank you.
So, if there is no queries, then maybe we can move forward and invite our next speaker, sir.
Yeah.
Okay. Thank you, Dr. Naik. And our next speaker of this session is Dr. Arijit Majumdar. I think he is not in participant list, but I see.
Good afternoon.
Okay, okay. Are you there? Okay, fine, sir. Sorry, sir. Okay. So our next speaker, Dr. Arijit Majumdar. Dr. Arijit Majumdar, he is from SAMI, Kolkata, and his presentation title is Millimeter Wave Technologies. So currently he is in charge of SAMI Kolkata Center, and he has more than 20 years of experience in design and development of microwave and millimeter wave components, subsystems and systems for different applications. So far, he has published more than 50 papers in different peer-reviewed international journals and conferences. So with this brief introduction, I invite Dr. Majumdar to deliver his talk. Yeah, Dr. Majumdar, please.
Yeah, good afternoon, everybody. I am sorry that I have to join late because of some other preoccupations. So I will be sharing my presentation. Is it visible?
Yes, sir, it's visible.
Yes, sir, it's visible. Sir, please make it presentation mode.
Yeah, I have made it full screen.
Yeah, fine, sir. Fine.
Good afternoon, everybody. So the exact topic of my talk, and there is no fault of the organizers, as I have sent the title of the topic much later than they have asked me to. It's actually the terahertz technologies for next generation communication systems. So before I proceed to the talk, there are two brief slides on our organization. Most of you probably know this, but still I'm just reiterating. Unfortunately. Okay, so Samir started from the applied group of Tata Institute of Fundamental Research in Mumbai in 1984, and now we have centers at Kolkata, Chennai, Guwahati, and Vizag, and they have been established at different points of time. The Kolkata Center specializes particularly on millimeter wave systems. We have been working on millimeter wave systems for almost past 15 years. And we have designed and developed different components and subsystems and delivered also it to different users. So if we see what are the focus areas of Samir as a whole, so we primarily focus on these four key areas: defense indigenization, next generation technologies, industry services, and societal solutions. So of course, today's topic is going to come under the next generation technologies, which we are all aware. So with this very brief introduction about the organization, I will go ahead. So if we see in the communication system, Samir has played a very key role in developing the indigenous 5G technology in the country. Samir has been part and parcel of the group which has designed and indigenously developed a 5G test bed in our country, and Samir has worked on the 28 gigahertz tiled array system which has been developed. So this experience gives Samir an unique opportunity. Whatever expertise and knowledge has been gained through the earlier project, that can be used for the next generation projects, which are probably going to come into the 6G technology, the 6th generation mobile wireless technology. And this technology is currently in a nascent state and is being proposed in the frequency range of 0.1 to 0.3 terahertz. Samir Kolkata has already worked up to 100 gigahertz, so we are taking up work in this area from 0.1 to 0.3 terahertz. So this is just for very brief, but I will not go into the basics because everybody is aware of it. But I'll just focus on the challenges of what are the challenges that we face in the country on implementing terahertz related research. So I am coming from a perspective where we come from microwave to millimeter wave to terahertz. So basically the route that we are taking is multiplying our way up from lower frequency to sub-terahertz and eventually terahertz frequencies. So the primary challenges are availability of semiconductor devices, test and measurement systems, access to precision fabrications facility, and of course the specific technical skills that is needed, which is very unique for this kind of design and development. And there are only few organizations in the country which is working in this particular domain. So it is very, very important that these organizations comes together, strengthen each other work, and then find out solution or implement technologies. Then primarily when this terahertz research has started in 1990s, there are two areas where this lower terahertz or the sub-terahertz work is being focused worldwide. Two areas are very, very important. One area is essentially imaging, where there is an FMCW system which has been demonstrated and developed for many, many different applications like concealed weapon detection and other kind of airport scanning applications. And it can create an image with very, very high resolution, even at a frequency of around 600 gigahertz or so. That is one application. And the second application is, of course, communication system, where the next generation, that is the 6G mobile wireless communication system, which is coming up and which is going to be the discussion of today's topic. So if I outline the topic, so essentially we'll talk about what are the basics about how entire world is thinking about this 6G mobile wireless communication, what are the expectations, what is the global scenario, the challenges and enablers, and what is the future roadmap, and how we can contribute in this research, or we are trying to contribute in this research in the country. So these are the current thoughts in the present 6G technology, that it's going to be very, very high data rate, much higher than what is called the FR2 of 5G millimeter wave band, which is in 28 gigahertz. Then intelligent reflecting surface, which enables beamforming for line of sight as well as non-line of sight communication, because it's been an experience in 5G that the high data rate millimeter wave band only works in line of sight scenarios, and the data rate rapidly drops once this line of sight is lost. Then, of course, this is going to be a new radio in terahertz band, like 5G new radio. This is going to be a 6G new radio, so that research needs to be done. Then terrestrial with satellite and airborne integration, that also is one target. Power efficiency, of course, a lot of AI and ML is going to come into this particular 6G technology, artificial machine learning. Full duplex system, which has not been yet implemented anywhere in the whole world. People are trying that to implement in the 6G, complete full duplex system without a TDM or an FDM. So that is people are trying. And of course, one key feature is going to be very, very high bandwidth, availability of very high bandwidth in this particular frequency range, which might necessitate a rethink of the strategies for the communication part, that is the baseband part of the technology. So if we see the expectation side from 3G to 4G and 5G and beyond. So if we take 5G, leave about 3G and 4G. 5G talks about connected things. So this IoT, Industry 4.0, all these terminologies, we have become aware, much aware. And it is trying to make sure that everything talks to everything. So all things are connected. So right from a light bulb to a switch to a power plug, they are all connected to some kind of a network, and some kind of a connectivity is given to the user to all these things. And this has got a very, very huge impact in Industry 4.0, where a lot of automation is going to come through this kind of very small IoT devices, which can actually progress into next generation manufacturing technologies. Now, the primary problem which people are facing in implementing Industry 4.0 using 5G technology is latency. The present latency is very high. The target was less than 10 millisecond, which has not been achieved yet in 5G. And in 6G, the target is less than a millisecond, which probably is going to, if achieved, then it is going to probably usher a new generation of manufacturing technology in Industry 4.0. So that is the target in 6G. And of course, the key word in 6G is connected intelligence, because everything which 6G touches will have AI and ML, artificial intelligence and machine learning. And we have seen the possibility of that in applications like ChatGPT. So the only question is that where that edge computing is going to be implemented, whether it will be cloud-based, it will be implemented in the device itself, how feasible it is to implement in the local device. These questions needs to be answered. But these are the targets of 6G wireless communication. Now, these are the expectations of 6G, where the networks are basically becoming sensors. So network itself is aware of its surroundings, and then it takes decision according to the surrounding or according to the behavior of participants. And then you have both line of sight and non-line of sight communication coming together. That is also one part of this 6G technology. And these are all projections from big network companies like Samsung or Huawei or Ericsson or Nokia. So though it is far ahead, the standard is going to come out in 2027. Potential rollout is in 2030. So we have a lot of time to do some research, participate in the worldwide research, and come out with some new ideas. These again a possible scenario where we have local users. They are connected to smart transportation users who are in a dead zone. We experience that, all of us, we experience that at some places the connectivity is very, very poor, which can be probably mitigated using things like intelligent reflecting surfaces or IRS, which is an interesting new antenna technology coming up. Then where it is possible, right now the satellite phone and the mobile phone, they are residing in different networks. So integration of these two is also one target which people are trying in the 6G technology, new 6G technology. And this is the spectrum and towards the TBPS communication. So this is the target of the TBPS. So if we forget about the top part of the slide and see the lower part, so you can see that there is a graph which shows that x-axis is where the complexity of the baseband modulation scheme is increasing, and y-axis is the bandwidth. So you can see with a very high order modulation scheme, even with certain amount of limited bandwidth, a very high data rate can be achieved, like 500 Gbps or 1 Tbps. But if the available bandwidth is much higher, then even with a much lower order modulation, that same kind of a bandwidth and same kind of a data rate can be achieved. And that is one of the way people are thinking about this 6G system. The reason being that in a higher order communication system, it becomes highly susceptible, higher order modulation system. It is highly susceptible to noise. And as we know that the noise floor will rise as we go high in the frequency, it may not be feasible to implement working very high order modulation scheme like a 1024 QAM or some such thing. So people may need to come down to some kind of a lower order modulation, which is implementable. But since the available bandwidth is going to be much higher than what is available now, a very high data rate is being targeted. So these are the technologies which is very important and coming up in the upcoming 6G. Terrestrial and non-terrestrial integration, communication and sensing, integration of that, distributed and deterministic network architecture. So essentially the network, we know that network can be either distributed or deterministic, but they can be intelligently mixed using AI and ML both. And then network security with native AI, this is going to be a very, very big question. And then there are physical technologies, physical layer technologies, which are very challenging, and people can have a very big research opportunity in this, like what I told is in-band full duplex technology, which doesn't exist in the world right now. There is a new multiplexing scheme called orthogonal angular multiplexing. So that is one configuration coming up, which can become revolutionary if implemented in antenna technologies. So these are new things which are coming up: reconfigurable intelligent surfaces, orbital angular momentum, and of course the fallout are going to be this kind of intelligent holographic radio, digital twins, AR, VR, real-time AR, VR. These kind of things are going to come. But this is still a very, very big challenge. We are only sensing the water. We do not know what is the depth of it. Probably in coming 5 to 7 years time, we'll come to know what is actually feasible, what is actually implementable. This is the global scenario. So in Japan, there is a 300 gigahertz band single chip CMOS transceiver developed by Hiroshima University with a 80 Gbps link demonstrated in 2019. Fujitsu Lab NTT, which is a big mobile service provider there, they have demonstrated 20 Gbps data transmission link at 300 gigahertz. This is for kiosk and instant data downloading applications. And they have taken a different approach. Instead of CMOS, they have gone for INP MMICs, indium phosphide MMICs. So these are kind of technology enablers for this kind of technology. Samsung is focusing more on 140 gigahertz band, and they have already developed a 120 element antenna array, phased array, in conjunction with California University, Santa Barbara, and they are showing a prototype. We have shown a prototype with 2 gigahertz bandwidth and adaptive beamforming, throughput of around 6.2 Gbps over a 15-meter distance. So these are some of the research which is being going on worldwide. In US global scenario, they have they have established 30 Gbps link in a very short, some millimeter distance. It has been established and shown the terahertz wireless link. China is also doing a lot of research, though the information which comes out from China is not very clear. But one report says that almost 100 to 200 Gbps link has been established using real-time terahertz in the 360 to 430 gigahertz wireless communication system, where this orbital angular momentum kind of a diversity scheme has been implemented in the antenna system, apart from the wireless link which is in the lower terahertz. So these are the technology needs and challenges which I have been highlighting in previous slides also, but I've just tried to summarize what are the needs and challenges. So one is the atmospheric absorption, which is generally high in certain frequencies, beam management and modeling. Then highly integrated devices. So device technology needs to come up a lot. Currently, people are trying with gallium arsenide, gallium nitride, indium phosphide, SiGe, and CMOS. These are like the enabling technologies, but I mean, nothing is final yet. People are continuing research, and I'll share some of the research in my slides, which comes hereafter. And then in the modulation, we are talking about this full duplex, orbital angular momentum, and this kind of multiplexing scenario. Antenna technology, we talk about this intelligent reflecting surface, in some cases lens antennas, etc., etc. And one big, very, very big challenge is when the data rate goes up, your processing speed needs to go up simultaneously. So that is a very big challenge for the people who are working in the baseband. That kind of a very high data rate, how that is going to be processed, and how that kind of data rate can be managed effectively. So that is also one big area for research. And of course, terrestrial and non-terrestrial communication system integration of both. So these are some of the technology needs and challenges. Some antenna technologies which is going to come up in this particular 6G scenario is intelligent reflecting surface, where user who is not in direct line of sight of another base station or another user, the signal can be redirected intelligently using AI, ML, and this kind of an intelligent reflecting surface, which can connect to users even when they are not in line of sight. So Samir has taken up one work in 140 gigahertz. So this is a work which is just started, sponsored by our own ministry, which aims to build a 140 gigahertz test bed along with a 140 gigahertz intelligent reflecting surface antenna to demonstrate the technology and the possibility in 6G. So this is the standardization part. So 5G, 5.5G is R18, which will start 6G. It has just vision now. And essentially, target is that by 2027, the 6G spectrum will be allocated. And then final specification is going to come up in 2030. So that is the target in the standardization part. And again, India is now a big part of the standardization ITU standardization body, and we are trying to carry out some research so that some input can be given to the 6G standards, the upcoming 6G standard, and India-specific concerns about this 6G wireless communication system can be taken care in the standard. And this is the Indian roadmap that we have started with sub-terahertz communication link at 140 gigahertz, which is a project we are running right now. Then terahertz transceiver design, which will translate into ICs, into terahertz frequency range, whether it's in 140 or even higher, up to 300 gigahertz. That also we will look into. Antenna technologies like IRS lens OEM and launch of terahertz test beds. And then the baseband technology comes after. Of course, packaging again is going to be a very big challenge at this frequency. So dedicated packaging facilities, which Samir also is trying to build for these terahertz ICs. That is also one area of research where people need to participate. So I'll just showcase in short some of the work that Samir has done. So we have designed and developed more than 30 MMICs in different frequency band from KU to W band. And they have also been packaged and integrated into different subsystems, which actually goes into deployable systems. So this is some of the indigenous millimeter wave system that Samir does. And that is why with a certain level of confidence, we have taken up this terahertz work, sub-terahertz work. I shouldn't say terahertz, it's primarily sub-terahertz work. So this is a sub-terahertz testbed for 6G communication, which we are aiming to make. This is the front end of the testbed, where basically we are trying to use a 5 to 7 gigahertz bandwidth right now for a 260 to 298 gigahertz final output, and which will be built in this kind of a block. So key components like subharmonic mixer, LO driver amplifier, power amplifier, these are in very high frequency, like in 129 gigahertz and then around 300 gigahertz. These needs indigenous development. We are trying to work towards this. These are some of the components highlighted, which will be used in the 300 gigahertz or sub 300 gigahertz test bed. So this requires indigenous development, and we are working towards that. Same for the receiver, it's very similar, only instead of an up conversion, there is a down conversion. So I'll not spend much time on this. And again, key components in the receiver side needs to be indigenously developed, where these kinds of research is still in a nascent stage in our country, right from device to packaging to final performance and interfacing, etc., etc. So we are just starting this. Then some of the device technologies which will be very important for terahertz is in the INP, indium phosphide and gallium arsenide technologies with a 35 to 50 nanometer gate length. IMHEMT or DHBT double heterojunction bipolar transistor, they are often the choice of devices due to lower noise and better gain performance. 6-meter indoor link has been shown by Fraunhofer Institute using above technologies up to 96 Gbps data transmission rate. But foundry access is key to develop this technology in-house or in-house development of foundry for this kind of technologies, which should be ideal, but only GATEC can comment on that in the today's forum. So these are things. So for example, I have shown these are the transmitter and the receiver chip using a 35 nanometer IMHEMT technology for indoor communication link up to 64 Gbps using a QPSK scheme at 300 GHz done by Fraunhofer technology. So these are the technologies we should be targeting and start working towards, and hopefully we'll be able to implement all of these in time. So with this, I come to the end of my presentation. Thank you. Open for questions.
Arjit, I have a question. You showed that some of the KU and MMIC and carbon and all that which you showed, that is your own design, and they
Yes.
are also developed in the country, or they are developed packaging also. You
No,
said you
they
did.
were all fabricated outside. Okay, we took
Not in
a
India.
foundry service. We used two outside foundry services. One is United Monolithic Semiconductor France. Another one is Win Semiconductor Taiwan.
Okay. But I'm thinking you could have used Anant Naik facility, which is.
Yeah. So, sir, recently we have visited
Had a
this
meeting
facility.
together.
Okay.
Yeah, I went there with
And
my team.
6G, what is the role of India in that 6G on user standardization? Apart from
Yes.
standardization, any role that is standardization means in terms of devices or protocols, or in terms of the standard for the interference ITR, ITU
Devices
regulations?
standard will not talk about device. The standardization means that it is the allocation of bandwidth and the protocol and the network architecture, and how the network architecture is being rolled out. That is the standard. But this research can enable us, which we are currently unfortunately not able to do, indigenously manufacture 6G network equipments in the country.
Correct.
Like we are lacking in manufacturing indigenous network equipments.
Is it because
Recently,
of manufacturing, or it is because of the architecture, the
no,
complexity
it's
is
because
not
we lack the manufacturing capability right now.
that is the foundry
Yes, that is foundry.
and the devices availability of devices and all that.
Exactly. So, like recently, Tata has taken up a step. They have bought that Tejas Networks, and they are trying to implement a foundry in the country where they are planning to manufacture all the 5G devices, so that the 5G network equipments can be manufactured in the country or even exported. So that is one step which is being taken. But 6G is like, I mean, it's still more complex, more challenging. So if we don't start now, we'll only be doing catch up.
Okay. Over to Lalitji.
Tata will only do the back-end packaging. They're not setting up any foundry as such. And yeah, definitely, like as I
Eventually
said,
they plan. So that's there. So, anyway, sir, I think you know what is the importance of the foundry. You being
Also, I wanted to ask
the helm
question,
of
I think.
yes.
Yeah,
And
all
I
the
agree.
past.
Like, but like you also need the funding, we also need funding.
exactly.
We don't get direct money from the government.
Yeah.
We have to take some project, some PO,
Yeah.
like ISRO and DRDO. ISRO is definitely a bigger partner to us.
So, just to inform the forum that when I visited, they have a very GATEC has a very interesting diode technology. So we are planning to use that high frequency diode technology for some of our sub-terahertz designs. So I am in the process with my own organization to sign an MOU with GATEC, so that that technology at GATEC can be leveraged for this kind of research.
Yeah, I think let's work together.
Dr. Rajiv, I would like to make a short comment.
Yep. Please,
So,
sir.
Arjit, you have presented a very wide overview of the global scenario and the efforts that are going at Samir. But I want to know that there are very sporadic efforts and here and there. But so far, have we been able to evolve a consortium approach or a national integrated program involving CDAT, your industry MIT, the GetEC Live Fabs?
Unfortunately, I
So
would say, sir,
there is need for doing that, but so far I think we are all working in our small silos and not coming together and
Yes.
bidding for a huge program in this area, which is the need of the hour.
Correct.
sir, my take would be that, like the programs that I have presented, we are collaborating with multiple IITs on those programs. In some of that. So, in sense, it's a consortium, but it's not wide enough. That consortium is not wide enough. So, this whatever you are telling is actually the need of the hour, but this requires a policy push. Okay, this is some kind of a policy which needs to be pushed from the ministry side. I think that then only it is feasible that a wider consortium can be built, and then people come together, share their knowledge, and then complement each other to develop end-to-end solutions.
We would very much like to have ideas on this, and we are also in touch with CDOT and all the IITs and so on, the joint center of DRDO and IIT at Delhi, yourself and others. So I would very much be happy to get your inputs, specific inputs on what should be done, which we can collate together and put up as a policy paper.
My humble submission would be that please talk to our Director General, Dr. Hanuman Rao.
He is very much part of the group. Yeah, because today he was supposed to be here, but somehow he's busy.
I know.
So I'm communicating through you that we would very much want to have specific inputs coming from you. Thank you.
I would put the message across.
Rajiv, I have got one comment here.
Please.
No, I was talking to Professor Paul Ross. We missed the 5G bust in India, and I'm sure what Arjit has made a presentation of up till 27, we are going to miss the 6G bus also. I had interaction with the various persons, academicians, mostly academicians in the country, who are talking about this. They themselves are not sure what is going to be the 6G. So can't there be at least a white paper in India where we can have this could be our approach for 6G, and then go abroad, talking to various industries and others. I mean, rather we ourselves are not clear. So I think we are going to miss the 6G bus also. If 27 is the target. Thank you.
Sir, my small input on whatever forums have been present in this in conjunction with DOT and our own ministry, MIT. Our government doesn't want to miss the bus this time. So that is why they are pushing for some research work in this. They are pushing for some funding, some real world work in this. And I think, as far as I know, DOT is going to come out with a white paper very, very soon on 6G.
Okay.
Some work is going on that.
Yeah, noted. I think there is a conducive atmosphere. You are saying that the policy, but what is
Yes.
apart from policy, what all consolidated effort has to be made? That also over the player, unless until the academia, whatever IITs and all that you are talking and your Samir can get connected with the industry, it will have its own impact will be less. That is what my view. Wherever industry is there, though they will be making a model in terms of marketable return on investment, but then the whole thing will churn only if we work in that direction. Unless and
I
the
agree.
should not be only with the IIT, then it should not be only with the research institute. Okay. Okay. Some question was there, I remember, from somebody that on graphene. What is the scope of graphene?
Any further question?
What is the scope of graphene material in advanced microsystem and 6G and antenna technology? And do you have answer to that?
Yeah. So basically,
I think I will put up differently. I will say what are the material requirement which will be which can be handled in a consortium way, in a definitely where our country has a strong can be made as a consolidated effort. In okay across
when
this.
we talk about this kind of high frequencies like 140 gigahertz or 270 gigahertz, then definitely whatever conventional material that we use, even in millimeter wave band, they may not work. I mean, most likely they will not work. So people have started working with materials not only in graphene, but there are other materials like LCP, the liquid crystal polymer, or even quartz. So these are potential candidates:
Okay.
graphene, liquid crystal polymers, and quartz. Potential candidate for application in these frequency areas. And some research I know is going on. I know that in IIT Rourkela, they are making antennas on graphene. Uh, I have been contacted with some of their professors for measurement
I
of
think
that.
that point is very clear, and I fully agree with Dr. Lalit that these are all small pockets. Some small work is being done. Yeah. Okay. Good. So that means it is also there are other material also like liquid, which you told. Okay. Okay. I think over to Veeraji.
Okay. Thank you, sir. Thank you, Dr. Majumdar, for your very insightful presentation. So next presentation in this session is from Professor S.S. Prabhu. So Professor Prabhu, his topic of presentation, development of terahertz spectroscopy and applications to the study of materials. So, Professor Prabhu is currently working as a professor of physics. His area of research interests are ultra-fast time-resolved phenomena in materials, terahertz spectroscopy of materials, metamaterials, high-field terahertz, near-field terahertz microscopy. So far, he has published more than 70 papers in international journals, several articles in many magazines, and more than 80 papers in different conferences, and has given several invited talks. So with this brief introduction, I am inviting Professor Prabhu to deliver his address.
So thank you, and thanks to all the organizers, especially Dr. Neeraj Kumar, for giving me this opportunity. And also, it's a great thing to listen to all the stalwarts. So I'll talk about a little bit about our institute. I'm from TIFR, which was formed by Homi Baba, supported by Mr. Tata, industrialist, and we are located in Mumbai's southern part, right next to the sea. And I developed this terahertz that almost 20 years back. And all these speakers have before me have already eased my work, so I don't have to tell much about the terahertz, but just very briefly, it lies between electronics and photonics. So there are a lot of applications in sensing, imaging, inspection, medical, etc. And you can see that main application of this would be in the imaging. So here you can see an image of a person who is carrying this dagger hidden inside. And also in the medicine, where you can actually see what is inside the tooth, etc. And for law enforcement, they are very much interested in this detection of these explosives like RDX, HMX, PET, TNT, etc. So if you look at the terahertz research globally, I mean, this is the data. I mean, it is continuously increasing. You can see the IEEE and Web of Science papers, and every year this number is increasing, almost running into thousands. And if you, those who are present here from the industry, for them the market of the terahertz is growing very rapidly. The rough change is roughly about 26%. So next 10 years, it is going to be quite a big market. And as already our previous speakers have shown that this is continuously going from 1G, 2G, 3G, 4G, now 5G, now into the 6G. And we need to actually look at these dominant technologies of 5G and 6Gs, which are going to come in, where the terahertz is going to play a very big role. Now there are several advantages of terahertz, that many large molecules have rotational vibrational energy levels in this range, so you can actually look at their spectra and figure out that the presence of these molecules, and therefore you can actually look at the inside of opaque items, because the terahertz can penetrate too. However, it is very sensitive to water, and therefore its range is very much limited. And therefore, all over the world, the main thing is going on towards generation of high intensity terahertz radiation. So the main issue is that there is heavy agitation in water, and therefore all our setups in the laboratory are put under nitrogen purge, and that is where the main problem comes. And our tabletop terahertz sources, which we have developed, they are into very weak intensities, but those are also all laser driven. Now, as I already mentioned to you, why terahertz? So the defense is much more interested in this, because to find out all these specific chemicals like explosives like RADX, TNT, HMX, because and PET, because they are very much having very specific spectra in those in the terahertz region. Now, these are some of these images which I've taken that, this is a picture of a normal shoe, and this is the picture of the terahertz image of this, and you can see that all these things which are hidden in the this part of the shoe are very easily visible in the terahertz, but the visible image does not show that. Same thing about the human being, where this person wearing all these clothes, he's hiding this dagger and the gun, and that is clearly visible in the terahertz. There are also these radar cross-section related studies on the F-35, which is currently the most number one stealth bomber from US Air Force, and this is a model which is 1:50 small model, and all its other parts remain the same. And you can see this is the cross section of this, and that is also compared with the F-16 model. That one shows a much better performance. Now, this is the map where I'm showing the terahertz sources, and as you can see, as you approach higher and higher frequencies, there is a sudden drop in the power which is emitted by these devices. So you have gun diodes, klestrons, BWOs, etc., impact diodes, etc. And the high power things which are operating here are basically QCLs, etc., or gas lasers. Gas lasers, of course, are very bulky. QCLs are small, but they need low temperatures for operation. And then you also have free electron lasers, which are really very massive structures, like which requires accelerator level. So these are really not practical. What we need is something which is handheld and very compact and very much useful. And these are all the source output power versus oscillation frequency. And you can see most of this work is gone into the gun diode formation or impact diode or tunnel diodes. And the powers are pretty low. As you can see that they are situated in the microwatts and milliwatt to microwatt. There has been a lot of funding in Europe and America for the development of these scanners. So there is a terahertz scanner which is at 94 gigahertz, which was made by this Millivision. And here you can see the human being which is standing in this unit, and you can find out that through his clothes this terahertz penetrate, and you can figure out these hidden objects. And this is the similar image of a man and a woman, and you can see that the entire body can be scanned. For higher frequencies, these images, like you can see that there is a dagger hidden inside this bag, and also this polystyrene foam, or as you call it, this is normally used by white colored thing, which is normally used decorations. So you can hide these kind of weapons inside, and they can still be detected at higher frequencies, or sub-terahertz as we call them. Now, there have been several technologies which are there for the detection of these explosives or other hidden things. So people have used animals or even X-ray high resolution, high mobility, mass spectrometry, etc. So some of these radiations are quite hazardous for the human being. Some of them actually require the sample to be destroyed or something to see its components. And many of these are really not useful for long exposures. So therefore, terahertz appears to be the best one because photon energy is very, very low. It can penetrate through opaque materials like clothes, etc. So it also becomes a much easier thing to use. And there are a lot of these vacuum electronic sources which are come up, the backward wave oscillator, extended fluxtrons, gyrotrons, etc. And CD Pilani, Dr. Neeraj Kumar is also an expert on this EWO and clustron and gyrotron kind of thing. So maybe he can also say a few words because he's there. The kind of sources that we have used or the kind of detectors that we have used are mainly laser driven. So here I will give you a brief things about our development. So first I will quickly tell you a little bit about our electro-optic terahertz detectors. So we just take this electro-optic crystal like zinc telluride and pass this pulse laser through this. And what happens is it passes through this lambda by 4 plate and a Wollaston prism where it splits it into two different polarizations which are balanced in the diode. And when you introduce the terahertz, there is a certain change of birefringence in this. And as a result, you have some linear polarization change and you have two different linear components which are separated in these two detectors. And then you vary this delay between the terahertz pulse and the red pulse, and then you detect the entire pulse. So these are there are several advantages of this because these diodes detect the difference in polarization and they are only limited by the phonon modes of this electro-optic crystal, and you get very high signal to noise ratio. So using these type of things, we have done some imaging in TIFR of the leaf. This leaf was kept in the standard envelope, brown envelope, and you can actually see that the image shows the water things inside. And along the edge, the water level is very low. So there you can see that the absorption is very, very low. Similarly, we had done this imaging of 500 rupee note. And you can see even the watermark is clearly visible. And Mahatma Gandhi's photograph is also clearly visible in this. We have made several terahertz components using different softwares. So we do the following. We first optimize these for given bands, etc., and then we fabricate them in house, and then we test them in our terahertz spectroscopy setup. All these terahertz spectroscopy setup, etc., are home built using TIFR. So here you can see that this is a T-shaped metamaterial which is acting like a filter, which is little narrow band around 1.1 terahertz. And we have also made these, frequency dependent polarizer, which you can see that there are certain bands it completely blocks and other bands it all allows all these things. So you can selectively also block certain bands in the terahertz region. We have also done, the controlling of dark quadruple modes in dolmen-like structures where, varying certain structures and certain modes, you can open up the windows in the given band, etc. So these are different types of filters and things that we have made. But the need of the hour is to have very sensitive broadband room temperature based high dynamic range reasonably priced detectors as well as very narrow band or widely tunable terahertz sources which are room temperature operable. And these should be again reasonably priced as well as it should be compact. So one can also do a lot of imaging using this. So our efforts have been on the photoconducting terahertz sources. The basic principle is you just generate electron hole pairs and then apply an electric field and accelerate them. So charged carriers which are accelerated will emit a terahertz radiation. So we take a semi-insulating LMR and we put these two electrodes, bias them, put this 100 or 10 femtosecond laser pulse. This is the red pulse, and then we these are electron holes are created in the gap, and then you accelerate them, and then you generate terahertz. So now, what are the things that you can modify in this? You can modify this bulk, that is the main crystal itself. You can modify electrodes with interdigitated plasmonic or different length, and modify also the surface. So based on that, we can generate different types of sources or detectors, and we can use them. So I'll briefly tell you. So we are using this commercially available, open market available semi-insulating gallium arsenide, but this low temperature gallium arsenide, we don't have any source, so we could not buy it. So this was that time, and now of course it is available at SSPL Delhi. So using the commercially available semi-insulating gallium arsenide wafers, we actually implanted them in our TIFR implanter, and then we made these devices. And you can see that the dark current of our implanted device is very, very low, almost 6 orders low. And when we irradiated, when we eliminated 125 milliwatt, it's actually took 2 orders lesser current than the semi-insulating gallium arsenide, which is undoped. And you can see that we could operate these, and the terahertz emission was almost 10 times higher than, this is the amplitude. So that means the power was 100 times more than the normal unirradiated sample. And unirradiated sample actually blew up below around 25 volts. But this sample continued to operate even beyond 120, 150 volts. We also used these to do the detection of the terahertz. So here is the zinc telluride based detection. This is the actual pulse. And then we reduce this carrier lifetime in semi-insulating gallium arsenide by different implantation, 10 to 13, 14, 15 kind of thing. And then we made these devices, and you can see the theoretically simulated curve and the actual measured current from these. They actually match pretty well. So we were quite successful in making the source as well as the detector, and these are all for the pulse terahertz. We also did this for the CW terahertz generation. So idea is very simple. You take these two 800 and 801 nanometer kind of two lasers, CW lasers. So we made this antenna in TIFR. We have a clean room where we fabricated this antenna on our semi-insulating gallium arsenide as well as implanted semi-insulating gallium arsenide. So once you put this in the gap, you will basically generate a difference photo mixing curve. So you can have omega 1 plus omega 2, which is a high frequency oscillation, and omega 1 minus omega 2, which is the envelope of this. So this envelope actually creates a carrier like grating, and this is almost like a time varying current which you are feeding it to this log periodic antenna, and then you bias it. You are just accelerating these, and you are basically emitting that specific frequency. So if you see the amount of current that was drawn by the unirradiated versus the irradiated thing, the irradiated ones were drawing much less current, 2 orders of magnitude current. And if you look at the terahertz power that we generated, so you can see it starts from around 200 gigahertz, and then it falls off up to 1100 gigahertz. While if you look at the unirradiated sample, we generated the terahertz that was actually already hitting the noise level. So ours went up pretty well beyond. So we also made these type of modification of the surface by putting in gold germanium rods embedded inside the same gallium arsenide, and using that we reduce the carrier lifetime. And you can see this is the device picture of our device which we made in TIFR, and then we also measured its emission, and you can see that this was actually engineered well with the simulation about all these designs where we wanted to reduce the carrier lifetime in here and also increase the emission broadband. So we have tried out various such designs. There are several. I can't really take care of all of those in such a short time. So to tell you very briefly that we had these laser-driven terahertz sources, but there are also several limitations of these. Limitations are the incident intensity. There are multiple iterative designs This can have fabrication issues. There are also, this fabrication needs nanotechnology needed infrastructure. And these actually have low optical to terahertz conversion efficiency. So we really have to work hard towards increasing these. And these are all laser driven, but they are very, very broadband. So that what that means is it generates broadband terahertz frequencies, and you can, of course, use all of them in together to generate higher power. We are continuously working towards that. And the way ahead that I see is that there are several applications, but very low uptake so far. If you can develop, high power sources, we can use those for long range explosive and chemical detection. And we can also, do what is known as the standoff imaging. And these imaging can be of, ceramic, foams, clothes, non-metallic items. There are penetrates through this, so anything hidden inside these materials you can find out. There have been new materials also like graphene and metamaterials and 2D other materials, which is a hot topic. We had made this graphene detector for ISRO few years back. It was again fabricated here in TIFR. And it also gave us a very good sensitivity. So there is a lot of scope for technology development and also development for this stress detection we use. Again, because of lack of time, I have not talked on this. Using what is known as a whispering gallery mode resonator. So for these, we use this same this type of unit. So where you can actually sit at one single frequency. And these are very, very narrow frequency ranges because this is again photo mixing effect. So one can do many things using these. And of course, this is all the team that I give credit to. And our current research that we have already developed this near field scanning terahertz microscope, where we can study, the near field of this. We have been developing these terahertz waveguides, terahertz fibers for these kind of detection, and also we use terahertz whispering gallery modes. And we are also looking at different terahertz crystals for generation and detection, which are more efficient. But now, because of the artificial intelligence based data mining and all that, this has become now a different game altogether. Again, I can't get too much into this because this will again become a big talk. And then we are now working on this optical form terahertz scope studies of different materials. We have started this, but this is of course out of scope for this talk. And we will get into these materials under high terahertz field. This is something that we are trying to develop because this would be very much useful for increasing the range of the terahertz, as well as we can probably do better detection. But these require again very high power amplifier type of lasers. And yeah, so these are all the things that we work on in a nutshell. So thank you very much for listening to me, and I also wish to thank the organizers once again, Dr. Dheeraj and others, for giving me this opportunity to say a few things about my work. So it's now open for discussions or comments.
I have only one question to you, Rajiv, here.
Yes, sir.
This program is funded by for a research for some application, or you
No. This is from DAE, Department of Atomic Energy, and we write projects for 5 years. And this is for, we are basically doing fundamental research on materials and development of these. So I'm developing this pulse terahertz technology for the study of carrier relaxation dynamics and those type of things. So in that we have developed many of these sources, detectors indigenously, because this technology, when I started, we were all under sanctions, or even now also we can't really buy low temperature gallium arsenide because that is again militarily controlled material. So now with SSPL, I do some collaborations. They have developed this LP gas. So I'm actually trying to develop the sources using that. These are all different things I do. and whichever other academic labs in the country which are there, I have helped them develop their gas.
It's all infrastructure, whatever requirement for your gas based, your source detectors, all are available, instrumentation and all that, for characterization and fabrication.
See, my group is small, so we have this condensed matter physics division, and there is a clean room which different people use for their different programs. So, for example, quantum communication, quantum computing people use it. Then this 2D material people use it. Then we use it for our terahertz thing. Then there is plasmonic group which they use it. There are other single photon detector. So different people are working on different problems from fundamental research point of view or science point of view. So they use it. But I have developed it also, this terahertz technology also, because there was nothing available that I could import. Everything was banned. So I had to develop everything in-house.
Okay, thank you.
Now, may I just intervene, Dr. Jyoti?
Yeah, please.
See, I think we are running little late, so I would request you to kindly manage time.
Yeah.
And we have questions. I think we'll definitely want to respond to them, but maybe at appropriate time. So I would request you to kindly wind up at this moment and with your summing up, and then we'll move to the next session.
Okay. I think, yeah, thank you very much. I'll just summarize that. I think most of the speakers have addressed the issues of one is technology, which is we are having in their on their ability, and the skill and the capex which is required. Three things have been handled. Like the first speaker, Dr. Shinde, was talking about the device, how the infrastructure and manpower and all those what can be optimized for multiple purpose rather than keeping it one. So that shows that this requirement of addressing some excellence center where everybody can approach, not only the industry but the other system people also. And then on the second was from that microwave, using the microwave devices for chilies and all those aggregators. I think that is very interesting, and I could gather only one information that this requirement is already peaked, and this, but I doubt that whether we have addressed all the requirement application in terms of we are only having the same L and S band and 200 to 300 kilowatt power, and that need to there area which can be explored in that. And the third one is the GAN and GAN, and then Schottky based devices, CAM and W band, and which Dr. Anand has explained. There also I find that lot of opportunities are there, but then the exploitation of utilization of those things by a number of other laboratory plus commercial application, which he said that it is, and for the academia, which has to be explored so that that can be used for multiple purposes. And then on the this 6G, that was another area which is well need to be addressed properly, and I think that is the area we should not miss, and that was discussed also during question. I think we need a consortium approach, and we need to have a discussion on that. And on terahertz, which was TIFR, I'm seeing a lot of interesting things are happening, but then utilization of these and then interlinking the science with the technology, which can be used for a application. That portion probably has to be done, because this also has a interesting application in terms of encryption key, which is required for quantum communication and for other application. I think these are the things which I could capture, and apart from that, I think we can all other MEM-based integration of all these technologies. We need to work on, and not only in technology level, at the consortium and the working groups, and the connecting with the industry. I think that's what I can summarize, and a lot of potential is there. Lot of different working groups are there in the country, and we need to join them together and make a meaningful outcome of this research as well as the effort which are being put into the various places, whether it is a receiver or it's an antenna or any other subject. Okay, I think that's what I want to summarize that. Thank you. Over to Bera.
Okay, thank you, sir. Thank you, sir, for chair this session, and thanks to all speakers for very interesting and insightful lecture. And with this, I just conclude this session and hand over this session to Professor Dixit for the panel discussion. Thank you.
Good afternoon to everyone who has joined this call or this workshop today. I'm Sandeep Chaturvedi, and I'll be moderating this interesting panel discussion on strategy for growth of RF microwave terahertz wave technology and industry in India. The previous session itself has been almost like a panel discussion, sort of, because we had the experts from various research centers across India, academia, industry, everywhere. But this, we are trying to have one more pool of experts coming in from industry, so that we can understand what is the need of the industry, what they look from the research institutions, what is the need of academia, what they need from the research institutions and government agencies to push this interesting field forward in India. So I would like to welcome on the panel Dr. A.K. Singh, who is ex-director of DLRL, and Dr. L. Ramakrishnan, CTO CRL, Bell. Sir, hope you are available.
Yeah, I am available. AK Singh.
If you can switch on your video, sir. So Dr. A.K. Singh is ex-director of Defense Electronics Research Laboratory, DLRL, Hyderabad, and led the lab awards development of towards development of state-of-art next-generation indigenous integrated EW systems for various platforms. For example, submarine, ship, ground vehicles, static installations, fighter aircrafts, UAVs, aerostats, missiles, and satellites. Dr. Singh has authored more than 150 research papers and 10 patents to his credit. He has been awarded NRDC, National Research Development Corporation Meritorious Invention Award in 1997, DRDO National Science Day Commendation, DRDO Technology Group Award in 2006, DRDO Award for Performance Excellence 2008, IET IRSI Award in 2009, DRDO Agni Award in 2011, and IET CDIEL Award in 2014. He is member of Society of Electronics Engineers and a fellow of IEEE. Welcome you, sir. If you can switch on your video for everybody to see. The co-chair for this session is Sri L. Ramakrishnan. Sri L. Ramakrishnan is currently Chief Scientist at Central Research Laboratory, Bharat Electronics Limited. Sri L. Ramakrishnan has put in around 34 years of professional experience in the field of defense R&D. He holds master's degree in electronics and communication. He has over 25 national and international paper publications to his credit, most of them in radar domain. He has filed and co-authored 5 patents as part of the team that has been credited with the prestigious Raksha Mantri's Award for Excellence in R&D under Innovation category during the year 2007-8 and Bell Excellence in R&D Awards during years 2007-8, 9-10 and 2013-14. He is associated with professional societies including IET and IEEE. Welcome you, sir, on the panel. Can we have both of you switch on your videos, please? And joining in the panel are the members from industry: Sri G.R. Shinde, GM Astra Microwaves Private Limited, Hyderabad; Sri Chandrasekhar, Recon India Private Limited, Bangalore; Sri Dr. P.C. Pancharia, Director, CSIR CE Pilani; Sri Nageshwar Rao, General Manager, Bell; Dr. Jayesh Kumar, Andhra Electronics Limited; and Mr. Monish Bhandari, Fortstar Medtech Limited. So we would like to hear from each of the panelists about their views on the theme of this panel discussion. And then I would request Dr. A.K. Singh, chair of the session, to take us through the session. Over to you, sir.
Yeah, thank you, Dr. Sandeep. So let us start the discussion. We have our panel members, Mr. G.R. Shinde, Dr. P.C. Kancharia, Dr. Adi Lakshmi, Sri Nageshwar Rao, and Sri Jayesh Kumar. Before we start, let me express my views on this. I come from a background of radar and electronic warfare system, and mostly currently we are working in the domain of starting from few megahertz to about 40 gigahertz. And there is a huge requirement of micro components, be it different type of MICs, power amplifiers, multifunction chips at component level, and then this need to be converted into modules and subsystems, and then finally systems. What I see that there are three major components. One is that design, then second one is the fabrication, and third one is testing and qualification. And in the previous section, most of things has been discussed. What I request from the panelists that what is that we are lacking, where we are lacking, and what is our strength and what is our weakness. So whether whatever strength we have got, like in my view, we have good strength in design, though we lack the fabrication facilities which is required to develop components for advanced applications. But we have good design, good designers available in the country, and also we have good testing and application testing infrastructure. Whether we are utilizing all our skills of design and testing and qualification and trying to develop the systems what is required, where whether these manpower or infrastructure or resources are getting fully utilized by the country. If I say the country, it means we have defense, we have space, we have academic institutions, and we have private industries, and then we have users. And everybody has got its own share. So we need to look that how efficiently what we have can be used, and then think of the upgradation of the facilities, what is required currently. So let us try to understand from the industry, their perspective, and try to see that how we can overcome or try to overcome the our limitations and what we can do next. So let us Sandeep.
So probably we can invite all the panelists one by one, and I would request Mr. G.R. Shinde to come online and express his views on the theme that Dr. Singh described. Sindaji, you are there? think he's not available, so probably we'll move on to Mr. Chandrasekhar from Recon for his views.
Yeah, good evening, all the dignitaries, and thanks for being, inviting me and being a part of the session. I really truly enjoyed in terms of the presentation, technical presentation done by all the different technical speakers, and certainly there's a lot of eye-opening things which I believe is there in terms of the technology. So, from whatever we want to look at from a search point of view, like in terms of strengths and weakness, yes, certainly, as India, we have grown in the last couple of years, and we have a lot of technical skills capabilities, and especially coming into now microwave and terahertz. Yes, this is going to be a new kind of technology which has been there, but we need to what do you call move it further from where we are as of today. I believe that the strengths point of view, yes, we have a good technical knowledge versus in terms of resources, yes, we do have that, and some to some extent, I believe from the knowledge what I have come across, yes, the testing capabilities, yes, there are some limitations, but certainly we will be able to make it up based on the need. However, from an industry's perspective, if you look at probably the weakness or probably the areas where we would like to get into a little more details is more like the visibility of where we are heading towards in next couple of years, and what is the need of that is something which I believe is may not be very clear. Probably it takes still some few more years to come down the line. And more than that, also from an investment perspective, how all these will culminate, to make this to make it, a successful, technology investment. So I would like to be, I'll be interested to just understand from that perspective where we would like to head in how many years, and what kind of investments could be a requirement here. Because as you, I think I'm not that expertised here, but still with the knowledge what I have, the investment is going to be in few millions of dollars. So so as an industry, certainly there's going to be a business point of view to be looked at as well. So I would be interested to know from that perspective, and that with that probably we will start working together with different industries or different partners and different technical people, so that we can all put this together and then see how we can work in conjunction with other support. That's my views on this, sir.
So I think Mr. Chandrasekhar has put the right perspective that we need to work on as a country to push the RF microwave field and the research in terahertz domain, which is the next big thing. As everybody says that we don't want to miss the 6G bus. And now we'll move on to Mr. Shinde. It is around now. Still not able to connect. Next, I would invite Dr. P.C. Pancharia, Director CSIR Siri Pilani, to express his views in the field of terahertz research. What's the need and what we can do next in his view.
Hello, this is Ayan Mandapadhyay. Actually, I think he has not joined yet because he has some other meetings.
Okay. So no problem. Then I will move to the next panelist, Shri Nageshwar Rao, General Manager, Bell, Bharat Electronics Limited.
Good evening, everybody. This is Nageshwar Rao. Actually, first of all, one major correction here. I am not general manager. So I am manager working in microwave tubes of components SBO. So I am limited to.
Organizers have promoted you already.
Yes, sir.
No
There is a big difference. Our CTO sir is also there. Okay, coming to my inputs. See, for any industry, not only RF and microwave, especially in this case, it is more relevant to defense industry. So for any industry, there should be a market existing. As an industry person, that is my view. And for the market to exist, especially in India, already market is there for this terahertz. I can see from previous technical talks. But thing is like time to market. That is one very much important thing for any industry to grow. And cost of production. These are the two things very much important. Otherwise, competition we cannot survive. One is time to market, other one is cost. So these two things, to cater to these two things, main important parameters like materials, raw materials. So how much of raw materials required for this technology is available in India? For production point of view, these are all very much important for an industry, defense industry like BEL. So first of all, having an ecosystem within India to manufacture bulk number of these terahertz modules or systems is very much necessary. That is one thing. And design wise, I think industry and then institute collaboration is of very much importance, very much important here. Anyway, institutes are developing, but making and are developing a prototype is not sufficient. Actually, making it productionized, making it a productionization is very much important. So that is what is gap I have seen in my tenure till now. So we should have an intermediate agency wherein that can bring items from prototype, that is research stage, to a productionization stage. So there is a slight gap existing. So something has to be filled up there. And next thing comes like skilled manpower. So when you go up like institutes to start courses on the terrorist technologies, maybe like it should be there a part of curriculum. Curriculum revision also should be there from time to time, so that latest technology should be a part of electives in the coursework of regular undergraduation, post-graduation courses. Yeah, these are the main points from my side at the initial stage. Thank you.
Thank you, Mr. Nageswara Rao. I would like to have now quick comment from our panel co-chair, Dr. L. Ramakrishnan, on the views from the panelists, as well a general comment on the theme and what he thinks of the scenario and how we can make strategy to move up.
So very good afternoon. Am I audible?
Yes, sir, you are audible.
Yeah. It's honor to co-chair with Dr. A.K. Singh sir. We had a good associations in Bangalore when sir was there here. Sir, good evening sir, and nice seeing you after a long time. And this microwaves and terahertz is going to play a very important role for the futuristic programs of our nation. There are 2-3 aspects. One is defense and security is paramount importance to Indian nation because they are going to affect the economic sovereignty of our country. So microwave technology and terahertz technology can play a major role in making India self-sufficient in protecting not only our borders but also for homeland security. For example, we have many technological applications from terahertz imaging which can be easily captured by various applications of homeland security, whether it could be a protection of very critical national installations like nuclear facilities, or it could be airports. So terahertz imaging plays a very, very important role. The second important aspect is space is becoming a very big opportunity. All of us should be aware of the program called Space Situational Awareness. So space throws a lot of opportunity, not only for surveillance and not only for surveillance and for communication as well as for the security. So there are many opportunities there. So microwaves plays a very important role. Optics plays a very important role in making the space situational awareness. Third important thing is the homeland security and our border security. So as Dr. A.K. Singh sir was telling, we have made a lot of inroads into the design area. So what is missing is maybe the component level, same case in the digital technology, at least in microwaves, making the components is not that expensive like setting up a semiconductor fab in the digital domain. So there should be an opportunity for all the industry players, including Bharat Electronics, to invest in the area of fabrication of microwave compound semiconductor. It could be on integrated photonics, so that the challenges of next decade can be faced. So these two topics are very important for our nation in terms of protecting our sovereignty, security, economic independence, as well as the space awareness. These are my comments. Handing over to you back to Mr. Chaturvedi.
Thank you very much, sir. I think you have correctly highlighted there are a lot of expertise available in RF microwave, and there is some gap, as I think many of the panelists in the panel and in the previous session also pointed out, that there is a gap between the opportunities and the players. So many times the collaboration issues, many times the funding issues, and I think it would be the apt time to for expert group or kind of work group to be established who can probably reach out to the policymakers to bridge these gaps. Next, I would like to invite Mr. Monish, who is bringing a different kind of flavor to this panel. He comes from the medtech industry, and we would like to hear what are the applications that they see of the RF and microwave technologies, and what are the challenges that they feel like from industry side perspective.
So yeah, good evening, August panel. I mean, I'm a master's from MIT, and we've been working on microwaves for medical waste since 2008. So we also have a transfer of technology from Samir Pavai, and we are now in a technology transfer with DRDO, DIAT. We work closely with Professor KP Ray. So that's a little bit of introduction about us, and we had the Honorable Prime Minister talking about us in terms of the development we made in PPE kits and N95 to be reused. So he had a 21-second exposure to us on his Mann Ki Baat last year, 2 years ago, sorry. So we've developed these modular microwaves with standalone units which replace autoclaves in hospitals. And this is a big technology drift, or I should say disruption, where autoclave uses almost 3,000 liters of water to sterilize with 3-phase 12 kilowatts power. Our systems work on domestic power line, single phase, and instead of that 3,000 liters, we use 5 liters of water per day. It's almost 800 ml. The technology is patented. We've developed further cycles to do infection control in 360-degree infection control and protection in a hospital. So we have special cycles developed wherein we can sterilize linen, we can reuse aprons, we can use PPE kits. And the good part is that all this has been validated by ICMR. In spite of doing all this, we find the biggest challenge, we've almost put in 10 years of research into this. I'm from Siemens. I have a Siemens background in medical research. And I was in Nuremberg before I came back and started this with Samir. So the biggest challenge is, while we are among the 4 such manufacturers in the world, and with the lead that India has in microwaves, I feel there is a lot that can instantly be done, because like I said, the water we save, the electricity we save, we work on a domestic power line, vis-a-vis 12 kilowatt 3-phase line, which is required for an autoclave. We have lakhs and lakhs of autoclaves working in India. So, but I feel that there is no regulatory as such. The only one we had was Samir, which had a patent on this technology, which expired 2 years ago or 1 year ago. And with that, we've had such a proliferation of people making microwaves across the country that the technology itself is becoming redundant. We are orphaned because there is no regulatory. So everybody, nook and corner, is making a device and says it's a microwave. Now, since we are dealing with something so critical, which means infection control, it talks about saving lives. So it's even more dangerous, because you do not know if the bag which has gone into the microwave is sterilized or not. So before this panel, I would like to know as to how we can regulate this industry technically, so that it's only a regulated or a validated product that comes into the market. And is there a group where we can join in to see how could this August panel help us in further developing the device? We also have a problem in hiring people who have microwave aptitude or intelligence. So we would want to hire, good experts in our factories. We have a factory in Jodhpur. We have a factory in Uttarakhand. Quickly, I'll tell you, we made some fantastic further developments because we worked with CSIR IIT, our Indian Institute of Toxicology Research, and we developed a crucible wherein we could create temperatures of 14 to 1600 degrees Celsius in a few seconds. And we used that technology for narcotics. So we called it MIND, which is microwave incineration of narcotic drugs. So you could actually place this at all the airports and harbors where you are able, contraband is caught, it could be destroyed at site with literally no residue. So this is what we've done. We need a lot of hand-holding in terms of technology. And at the same time, we would want this panel to address the issue of regulatory in this country. Otherwise, this orphan technology with all its attributes could be just another thing in a few years. Thank you very much.
So thank you very much, Mr. Monish. Actually, you have brought two very important things that probably most of the industry people look for. One is the regulation and use of these technologies. There are plenty of technologies, my MW expertise available, but regulation of these technologies when it goes to civilian domain, because most of this has been mostly limited to defense and space applications. But when it goes to civilian domain, we do need regulations. That's very important point. The other point that you brought out was trained manpower for microwave and RF feeds. This is something which had been a pain point for many years. And I think now we see some concentrated efforts. I represent IEEE Microwave Theory and Techniques Society from Hyderabad chapter, and we are making a lot of efforts in past 2 to 3 years. We are trying to attract students to this subject. We are trying to impart to them a lot of knowledge in simpler way so that they are not afraid of entering into the field. And also we are trying to attract them to the subject by more hands-on kind of training by collaborating with various institutes. And I'm hoping that in the next 2 to 3 years probably you will have some closer on this kind of a problem where you're not able to get enough microwave engineers coming out of the colleges. So that's very important point. And I would now request Dr. Singh to make a quick comment on the various aspects that the panelists have covered.
Sandeep, one thing like Dr. Monish brought out on the regulations. So presently, we don't have any process in place. So may I request, whether it's possible or not, I don't know, make a proposal from INA itself to the government to bring out some regulatory some regulations to this kind of usage of devices, microwave devices.
Yes, I think Dr. Singh, that's very important. That's very important. And if we could, I'm sorry to interrupt, sir, but if we could have a common portal where we could contribute towards microwave. This is potential. I've worked on it for 15 years now. I have almost 35 years of experience in the medical fraternity. And I feel that this is crazy what it could do. And India has a clear advantage over everybody else. Can you imagine an industry which is not there in China and Korea or anywhere across the globe, except between Austria, French, and India? So we are way ahead, and I owe this to Sameer and DRDO, Professor KP Ray, people in Sameer who've taken it so far. Now it's for us to consolidate our position in India and abroad. Why can't we make this and export it to the world? This is what the country wants today. And super sustainability. I mean, literally zero power. Zero power, zero water.
Yeah, we understand your point. So may I have, can we have some comment from Dr. Lalit Kumar, sir? If he's there.
Sir, you are on mute, I guess.
No?
I don't know, Dr. Lalit Kumar. Dr. Lalit Kumar, we are waiting for your comments on this regulation part.
I think he may not be there, but that.
Yeah, actually, I was having some issue with the communication. I would like to say that once again, this is echo is coming. Just hold. I think there is some echo here.
So actually, there is some audio issues in the bits part. So they are just sorting it out. So they will be rejoining in 1 or 2 minutes.
Okay, so in the meantime, but sir, probably we can invite Director CS Siri to put up his views.
Yeah.
Sir?
We can invite him if he's there.
Yeah, he's there. Dr. Pancharia, good evening, sir. Welcome on the panel. And I'm not sure if you heard some of the views from the panelists. We would like to hear what we can do better in microwave technologies in increasing the penetration of microwave technologies to more and more civilian applications, and what are the challenges that you face, and what, because we some of us are in the government bodies, so how we can help ease the situation.
Yeah, thank you very much. All respected INA members, Dr. Lalit Kumar, Dr. A.K. Singh, all the faculties from different universities, students. Thank you very much for asking for comments on microwave. Though I am not from this field, I belong to instrumentation side. So, but being a scientist in Siri, I know a little bit about microwave. And now heading this institute, so it's my responsibility to share what we are doing at our institute. So this is a time, now it's a time for microwave systems, not for the devices. In fact, last 7 decades, we have been working on microwave devices. We have successfully developed number of microwave devices. But if you look at the present scenario, like in India, Atmanirbhar Bharat, so it's the right time for microwave systems. In the same time, solid-state microwave. You know that microwave systems, microwave devices traditional devices, they have importance. At the same time, there are some limitations, like lifetime, like their uniformity. A lot of issues are there. So there is a right time that we should shift from traditional to, at least for low power in solid state microwave devices. Nowadays we are having this magnetron in microwave oven. So I think next 5-10 years there will be solid state microwave oven. So we should, with the time, we should move towards this solid state too. But it has a number of applications. What Siri is doing, I think all the society knows that we have been working on magnetrons, klystrons. So it is well known. This is the right time that microwave can be applied to the different systems like agro-based industries where still dryers are required. So microwave dryer or drying process, that can be one aspect in agriculture, which is huge scope for essential oil extraction. Siri is working on this, and recently the hydrogen generation. Hydrogen mission required a microwave systems. So how can we use microwave for generation of hydrogen? How can we use this for methane cracking? How can we use for plastic waste sorting, plastic waste, then biomass gasifiers? So these are the field where we are working, and we already initiated these activities at our institute. Now, hopefully by end of this year, there will be multiple systems for demonstration. So already we have started in 2020, almost 2 years. So now it's time for prototype development. Then I can find number of products based on microwave, like muffle furnace. It's the one field where any Indian company, Indian scientists, they should develop this muffle furnace. The sample digestion unit is also microwave-based systems. This is a huge scope in different fields. So we are also working on like a hard killing of drones. It is using microwaves. This is a big scope, and this is a national requirement. So we should also think on that, how we can use killing of drones using microwave, high power microwaves. And the plastic problems, we know that everywhere there is a plastic. So can we use microwave as a pyrolysis or carbon generation or some biomass gasifier type of thing that can be used for societal applications? All are burning issues. I think all the society, microwave society, should focus on this. How can we develop the systems which is directly relevant to our society and their problems? So this is all we are working in institute, apart from the traditional the work we are doing at Siri. Thank you very much for giving me this opportunity to share our work to you. And any type of this development or any type of research work related to microwave, if required, we are always ready to contribute in this. Thank you very much.
Thank you very much, sir, for highlighting a sort of non-conventional use cases for microwave technologies. I'm sure there are a lot of researchers working in this area. We call it microwave for life sciences, basically, where we try to address use of microwave technologies for various healthcare applications, where various kind of sanitation applications, etc. So already plenty of people working there, especially you mentioned about micro oven. Probably we may not have to wait 5-10 years. Already there are some reports where some of the prototypes realized using solid state devices because you need something like 1 kilowatt of power, and these days gallium nitride based devices are available to produce that kind of power. And if I'm not wrong, already some prototypes have been demonstrated using solid state devices for microwave oven or heating purpose in general. So thank you very much, sir. So next I would like to invite Dr. Jayesh.
Hello, can you hear me, sir?
Yes.
Hello. Can you hear us?
Yes, yes, we can hear you.
Yeah,
Yes,
okay.
go on, please.
Okay,
So
okay.
Jayesh is a very young RF engineer. He has passed out from BITS Hyderabad and is part of Andhra Electronics, working in high power circulator isolator field. And probably it's a good contrast in this panel to have a young voice, young technology speak about this.
So thank you very much, Sandeep sir. So good evening to all. So first of all, I would like to thank the organizer for inviting me. So as a first of all, as a industrial, what we are facing that as Sindhu sir already discussed the manpower and also Sandeep sir mentioned the manpower, but not only the manpower, so the skilled man. It is there. So skilled manpower. So generally, the whatever the employees are working, those are only the basic. Their graduations are from diploma and the degree. So, but they know how to measure the equipment and any components given to them. They can easily measure. But what are the parameters they are measuring? Some parameter they can measure, but what is the meaning of that? So they even don't know. So the skill and so that some type of training or something. If so, the microwave subject, if it is a thought from the colleges or academics, so that students get attracted towards this subject. So academic, if some type of institution from academic institution and some societies, so they can provide such type of training to the employees as well as students, so they can increase their skills in this RF microwave. And one more point I would like to raise that so as a industrial where we can invest the things so that we will so we'll get more opportunities to develop this RF domain, and it would be very difficult to afford the testing facilities on all these things. So it would be good if some other labs and so that they can provide so on the sharing base means we can test our components and so that and also the um, some type of collaborations it would be required for industrial academic, because industrial they cannot spend that much of time in the R&D or so that so if such type of if India industrial academic collaboration will there, so that research and because theory and if practical both can merge together, then we can develop the things very fastly. And during the development in the RF domain, again we recently we are facing the challenges, that is the material also, because most of in the RF domain whatever the materials we are using, that those are importing from some other countries. So if we have to more focusing on this material production in India, so itself so we can develop all the components very fast. So these are the some points just I would like to discuss. So first, and thank you all, thank you very much.
Thank you, Jayesh, for bringing out some of the challenges that educational institutes, researchers in the educational institutes, and new industry or startups. I think so. There is a call for basically volunteering experts, like experts in the micro industry who can volunteer and share their experience and knowledge with the educational institutes, associating with the students. There is a call for the higher institutes working in RF and microwave area with good resources for measurement or fabrication to extend their facilities on of course, based on their convenience, so that the researchers can work on those setups and then carry out their research and produce the results that we all look for. So with this, probably I would before I request Dr. Singh to sum up the session, we will probably hear from Dr. Lalit Kumar on his views about the regulatory affairs for percolation of microwave technologies into the civilian domain.
Okay, thank you very much, Sandeep. So, can you hear me, all of you?
Yes, sir, we can hear.
Yes, good. So, I think we heard a lot of good views, and one of the things which always bothers us is that India is such a vast country, has such vast talent distributed in various institutions, excellent facilities, excellent design technologies, as Dr. A.K. Singh pointed out. But still, I think somewhere the complete innovation cycle, what it requires is that from concept to market, there are missing links there. And that's the reason we are not able to really make a mark in the domain which we are capable of. So there is a huge requirement for all of us to come out of our domain and work together in a consortium manner from academia, industry, R&D, user, customer, whosoever is there. All of us should make a team and work together. Then only we can make some progress in this field. So this is just a comment which I thought, whatever this recent speakers have spoken, and a consortia of facilities to be also developed to be able to share the facilities. And the biggest thing is that we do not know really what is needed. Everybody keeps the requirement to himself. So, for example, if Bell, the CRL CTO is there, if Bell needs 100 type of components which need to be used in the system that you produce, is there a list of those components or subsystems or super components, whatever? Is it available on your portal so that somebody who wants to take the courage of developing or producing them or adapting from whatever one can import and then value add whatever. So that kind of information is not available from ECL, from Bell, from BEML, HAL, whichever you say, such information doesn't become easily available. So that is one area where I think all of us can work together. The standardization of the products is a very important thing, and Monish has pointed out the BIS has the responsibility of generating all such standards, and they do have a standard for the microwave oven. Now, whether that same standard will apply to a medical system is not definitely straightforward. So, whenever such new products come in India, there are panel of specialists in BIS, and I think we will definitely take this recommendation our list to propose. But one can definitely approach ab initio to BIS to see whether they have any existing standards. If they do not have, they usually have an ongoing process by which they keep on developing new standards for new products being produced in India or being imported in India also. So if the products are imported, they also have to conform to BIS standards, as you know. So this is, I think, some comments which I thought to the latest remarks which were made, I just would like to say. Thank you. Over to the chairman.
Thank you very much, sir. I think we have already overshot by more than 10 minutes, but it has been a very thought-provoking panel discussion. I'm sure that the expert group at INAE would probably take it forward in terms of approaching to the regulatory agencies, the planning agencies. And now I would like to take a quick comment from the co-chair of the session, and then I will request Dr. A.K. Singh, chair of the session, to conclude the session, please. Dr. Ramakrishnan. think is not available, sir. Then probably we'd I'll request you to sum up the session and then we can wind it up, sir.
I think, Dr. A.K. Singh, I would request you to see that if there is anybody among the audience who would still want to make comment, we can spend a few more minutes, I think.
Yeah.
Yeah, Dr. Singh, I'm Paul here. I wish to make one comment. You know, Mr. Monas talked about the trained manpower. There is a problem of trained manpower. You know it. I know it. We have to force the persons to work in the field of RF. And now RF has become an elective under the NEP 2020 or maybe new curriculum in most of the engineering colleges. So it will be difficult. However, what I tell Dr. Lalit Kumar, we can put in our recommendations, I mean, at least a group which I headed for the education and other things, that if there is a requirement by the industries, maybe a 2-week course can be arranged by INA in Bangalore, because Bangalore has got the maximum number of RF persons, and a course can be built for them, and a 2-week intensive course can be given. We can introduce the persons to microwaves and also for the measurements. So we cannot get the trained manpower from the various colleges. Another thing, since I had also a small duration of period as an academician, and I have gone through IITs and everywhere else, etc. The research which they are doing is in a very narrow field, and mostly that field is not of much use to the industry which we have talked about today. So, if it's needed, perhaps this INE working group can take a lead, and we can create a 2 weeks course for them, and in Bangalore, and an intensive training can be given. So that's the only thing can be done to help the industry presently, because I had been sitting since morning looking up. I mean, I heard the GATEC, I heard APMML, I heard, Dr. Pancharia and everybody. So I feel there is a requirement for trained manpower, but whatsoever manpower is available with them, that can be trained rather than looking from the colleges, because college is difficult now. And with NEP 2020, somebody can come out, a electrical engineer can become a commerce student, and commerce student can become an electrical engineer. So, I mean, I don't want to further comment on that. Thank you very much.
Thank you, sir. Brought out you shared with important is that are not trained. They can be trained only when they are working in. That is, we must understand. As Paul sir suggested that if there is a requirement,
The voice is breaking. I think you may have to adjust your microphone a little bit. Voice is not coming clear.
am I audible?
Yes, sir, you're audible now.
Yeah. So what I'm trying to say that if there is a requirement from industry side, what Dr. Paul sir suggested, there can be tailored courses to train the working level people. So
Sure.
Okay.
So that is important suggestion. And to conclude this session, as all of us listened, two things came very clearly, that one is that trained manpower, second is that whether this test facilities can be shared, because these two things are requirement from the industry side. And now there are talks going on that whatever facilities the DPU are having, that should be shared with the industry. So that can be that is in process. And second thing is that from industry side that what is the market potential and what is the business perspective. As all of us know that there is huge requirement of microwave components at various levels, at least for defense and space applications. Earlier, the most of the components were developed for defense and space applications, and then that were transferred to the civil applications. Now, reverse way it is happening. Whatever is being developed for civil applications, it is getting used for defense and defense applications. So, requirement is huge. We have strength in the design. We have strength in making subsystems and systems. Only we need to see that all of us together as a government R&D organization, as a industry, as a academia, we should always work together to ensure that whatever strength we have, we should be fully utilizing that. So with this, I would like to conclude this session.
Thank you very much, sir. And thank you all the panelists and all the esteemed speakers.
I'm sorry to intrude, sir. I think Ramakrishna sir from BL co-chair also has joined. There was some technical issue. Maybe we can invite closing comments from him and then conclude.
Dr. Ramakrishna, if you're available, you can just give your closing comments, sir.
So, are you able to hear me?
Yes, yes.
Yeah. So, thanks for inviting to this wonderful webinar. So, Bharat Electronics always supports the ecosystem. It could be a collaborative R&D or the small industries or startups. We are there actually. We are only helping that. But the suggestion given by Dr. Lalit Kumar will take it up. And is there any way to display the requirements? There are huge requirements of component development, and we work with all these industrial names which we are hearing here, whether it be Amla Electronics or Astra Microwave. You name anybody, we are there with them. We are already collaborating with them. But as Sarah pointed out, we can also extend in our portal what kind of generic requirement. That is one way we can think of. I just brief to our internal authorities. Number two, yes, there are possibilities of sharing the test facilities. Already we are doing on a commercial basis, but there are opportunities where there is a collaborative work happens. Certainly we can share instrumentation. For example, we have 110 gigahertz, network, things like that. For so from microwave or photonic side, we have best instrumentation available. Certainly, but because of this, what do you call that, vigilance and other rules, we cannot, we have to give equal opportunity to all the players in the field. So we will see how best we can collaborate and offer the facilities what we have. Already we are doing that. So these are all my comments, and collaborative R&D is certainly the thing which Bharat Electronics is taking up. Industry partners are most welcome. And I am also excited to see the kind of work done by TAFR, Mits Pirani, Siri Pirani, all these people. So we will be joining hands with them and take the kind of technology forward. Thank you so much for the opportunity, man. Thank you so much.
Thank you very much, sir. So I thank both the session chair and session co-chair for leading us through this wonderful panel discussion. And also to all the panelists who have expressed their views, so that like we basically cover the whole spectrum of requirements.
Dr. Sandeep, should we invite a few questions, one or two questions from the floor or from the audience in case anybody wants to ask? Probably they can
definitely.
mention.
We asked, opened the floor, but
yes.
If there is anybody still who has some questions, probably we can take one or two.
Yeah, if anybody from the audience wants to ask, probably in the chat box you can, or raise your hands. You can probably raise your hands and we'll unmute you all.
Hello.
Yes, sir.
This is Anirban Bera from CSIR Siri Pilani. Actually, not my query is just one submission to Dr. Monish from that industry. Actually, our directors have also mentioned the same thing. Now we are doing some system level, microwave-based system level research. And if Dr. Monish is willing to visit our lab, I just invite you on behalf of our institute. You can visit us and maybe you can visit what we are doing and we can discuss more in this regard. Okay, thank you.
Thank you, sir. Yeah. Any other questions from anybody? Dr. Richards, I think you have sent some message. You can probably, we have unmuted. We have, I think, yeah, I think you can unmute, you can speak, sir. Dr. Richards, you have, I think, written a message.
Kindly, am I audible, sir?
Yes, sir, you're audible.
Yes, sir. So, kindly create a web page with details of the facilities and the respective specifications and the links so that all the industries, academic and research institutions would greatly benefit if it is possible with the INA. That would be greatly beneficial, sir.
I would like to respond. Definitely, INA group can try to do that, specifically for microwave to terahertz. But I understand that in ISC Bangalore, there is a institute which has been opened with government support, which is already doing this kind of a job of making a kind of a consolidated compendium of facilities and facilitating the sharing of facilities in academic institutions to the industry and R&D people. So I think you can try to look at that. I think all of the participants, I think I would suggest to look at that institute in ISC Bangalore.
Okay, even I would like to make a comment here on, I think a lot of panelists have also spoken about the need for trained manpower who can actually understand what they are doing. And in this regard, I'd like to submit to the esteemed audience that we are now also trying to develop a program for hands-on training of people in this RF and microwave domain. And we are trying to do it both for people who are still at college and for people who are working in industry for some in-plant training kind of a thing. And we are in talks with a few industries for this, and I think in the next couple of months we should be able to come out with some sort of a curriculum which would probably help out at least to some extent in this domain. So that is my submission to the panel. So I think unless there are any other questions, Sandeep sir, you can conclude the session then.
Yeah, so I think then probably we'll see the audience can always reach out to the organizing team if there are more questions or any specific inputs or suggestions that they need to see. With this, I would like to thank everyone for being part of this panel and to the audience also for patiently hearing and I think we have been almost 3 hours into this webinar now, and I hand back to the organizing team for the next part.
Okay, thank you, Dr. Sandeep. I would now like to invite Dr. Anuj Bhatnagar from Samir to please deliver the concluding address for the seminar.
Hello, thank you very much. I hope I am audible.
Yes, sir, you're audible.
Yeah, fine. Actually, today's webinar was very special in the sense I could make out that within 4 hours, speakers, eminent speakers from various organizations representing R&D, academics, industry, as well as the user agencies like DRDO and ISRO sectors made presentations or the facilities research work which they are carrying out, covering 3 wide areas, which is microwave, millimeter wave, as well as terahertz. So it is excellent in that manner that within a short span of time, everybody, all the participants who attended the today's webinar, they got a general overview about this area, basically the state of art work which different organizations or research groups are doing as on date, and also the industry what they are working, at least some part of the industries who participated in today's event. There are few things which I noticed. In fact, some speakers have also pointed it out that all the organizations are doing excellent work, in these high-tech areas. But and industry also is trying to do their best. There is some sort of a disconnect, or not disconnect, I will say more need to be done in the way where different organizations come together and try to synergize their activities, their resources.
I think a connectivity issue is there on Dr. Anuj's side. Yeah, I think some connectivity issue is there. Maybe Dr. Neeraj can continue.
Am I audible, sir?
Yes, you're audible.
Thank you, sir. It's my privilege to propose vote of thanks here. It was third webinar which is being organized by INE Expert Group in collaboration with Siri, BITS and other prestigious institutions. We had two technical sessions. First of all, I would like to thank Dr. Ajit Jyoti sir, Director in Space, for accepting our invitation and chairing the first session with theme Microwave, Terawave Technology and Industry Perspective. I would also like to thank Dr. Anirban Beraji for coordinating the first session. In the first session, there were eminent experts who touched upon different aspects of microwave and THz technology, starting with Chairman Dr. Rajiv Jyoti sir, Dr. Sinde sir, Dr. Anand Nayak sir, Dr. Sam Reddy, then Dr. Majumdar sir, Professor Prabhu. Thank you, sir, for your valuable input. While in session 2, there was very good panel discussion. First of all, I would like to thank Dr. A.K. Singh sir for accepting our invitation and chairing the session. Thanks are also due to Dr. L. Ramakrishnan sir for co-chairing this session, and also moderator Dr. Sandeep Chaturvedi ji. I would also like to thank all the eminent experts who participated, starting from Dr. Chandrasekhar ji, Sri N. Rao ji, then Dr. Monish, then PC Pancharia sir, Dr. G. I. Jayes ji, then Anuj Bhatnagar sir for his concluding remarks. Thank you, sir, for your valuable inputs and remarks. From the organizing committee side, I would like to thank first of all Lalit Kumar sir, Chairman INE Expert Group, who is the key person behind this webinar. Also, I would like to thank Professor Harish Dikshit ji and his wonderful team, and Dr. Ayan Bandyopadhyay sir for putting their valuable efforts in organizing this webinar. Last but not the least, I would like to thank all the participants for their time and valuable presence. Thank you one and all.
So I think it's not on agenda, but I think I'll take this privilege to thank each and everyone, including the participants who have made this wonderful event highly educating for me and for, I think, many of us. And I would like to say that this is just coming together is the beginning. We should continue. Your email addresses and the contacts are there with the committee. And we should continue this interaction to develop the idea of growth of the microwave, millimeter wave, terahertz industry and technology in India. And the ideas on this, which may come later, or anybody who did not get opportunity to express ideas or views on this, is most welcome to communicate with us and keep connected. So we would like to continue this interaction with you and get more inputs to make a recommendation or a framework, I would say, which will facilitate the objectives with which we have started of knitting together academia, R&D, industry, users and all the stakeholders, policymakers included, to say that we really make a dent in the Make in India, in the micro millimeter wave and terahertz technology, because this is the future. This century, as I said in the beginning, will be driven by this, and India should not be left behind. So we should definitely work together to make it a good, successful effort, and hope that we will be able to make a difference little by little, drop by drop. If you contribute, we'll be able to make a difference. Thank you very much. Thanks you one and all. Thank you.
Yeah, I'd like to request all the speakers who have presented to please send in their presentations to me so that we can make a proceedings out of this. And I would also request all the participants that we would be sending you a feedback form to please fill that up. And in response of that, the participation certificates would be given. I think with that, we can thank you very much for participating in the webinar. Thank you very much for your time. With that, I think we can conclude. Thank you. We can, I think, conclude.